it can be saved and people can access it for the recording. Okay. All right. Okay, let's just see.
Okay, it should started now.
We're running now. Okay. All right. I
will
think
pass the
for the
host
co-host, you return the co-host to me. Okay, good. All right, admitting the participants coming, and there will be co-hosts also who organize the traffic who will come in during our presentation. So it should not disturb the running of the presentation. Okay, I think we should start. It's already 2 as we try to be on time. Now I would like to give it to the MC. So as for your information, this tutorial series for this session, for this 5th one, is hosted by Hasanuddin University. So we are arranging it with the students as well. So my student will be the MC and some of them become the co-host, and I will be moderating the session. Okay, Nisa, we can start that for the ceremony. Time is yours now. Yes, okay.
Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to all invited speakers, distinguished ladies and gentlemen, audiences of this Asia Pacific Synthetic Aperture Radar APSAR 2021 pre-conference tutorial 5th, which is the last of the tutorial series. Allow me, as part of Hasanuddin University host team, as the Master of Ceremony. My name is Anissa Ramadhani, a student of Faculty of Engineering, Hasanuddin University. Ladies and gentlemen, and online SAR tutorial audiences, our tutorial today will present 3 speakers who are well known for their expertise in the field of SAR and its applications. They are Professor Avik Bhattacharya from Indian Institute of Technology, Bombay, India, with the topic of information extraction from polarimetric SAR data. And the second is Professor Masanobu Shimada from Tokyo Denki University, Japan, with the topic of SAR Interferometry Basics and Application. And our third speaker is Professor Steven Gao from Kent University, United of Kingdoms, with the topic of antennas for synthetic aperture radars. The tutorial session will be moderated by Dr. Ilham Alimuddin, a lecturer of Geological Engineering Department, Hasanuddin University, who happened to be an alumni from Chiba University. Our moderator is Sir Ilham Alimuddin, MGs, PhD from Hasanuddin University. Ladies and gentlemen, let us welcome and listen to the opening speech of the last tutorial series delivered by the General Chair of the APSAR 2021 conference, Professor Dr. Josaphat Tetuko Sri Sumantyo. Time is yours, sir.
Thank you very much. Yes, you can hear my voice?
Yeah? Yes, loud and clear, Professor Jos.
Okay, thank you very much. Yes, first is I want to thanks to Dr. Ilham, who managed this tutorial, and all of the team, yes, that support to realize this event. Yeah, and also here is Dr. Agustan, the chief of the head of the Indonesian Remote Sensing Society. Thank you very much to attend our tutorial, and also Professor Avik. Yes, it is also my friend that always support our activity. Yes, thank you very much to give the tutorial today. And I think later Professor Shimada and also Professor Steven Gao that also support our activity, especially in the synthetic aperture radar development for the long time. Yes. Today, I'm as the general chair of this Asia Pacific Conference on Synthetic Aperture Radar 2021. Yeah, that the symposium, the APSAR 2021 will be held in Bali Island, Indonesia, in November 1st to 5th, 2021. And now we prepare actively to realize this symposium, including this pre-conference. Yes, and then yes, we still see and waiting the condition of the COVID-19. Yes, and I hope we can do in-phase, yes, in Bali Island. Yes, but if in the worst case, as we will continue in using the online symposium. Yeah. Okay, it is the you can see that it is the call for paper of this Aperture 2021, and you can see the detail in this sorry in this website. Yes, Aperture2021.org for the detail, and we still waiting for the full paper. Even you not yet submitted the abstract, it is still we open, and right now we already get more than 150 paper, yes, from around the world. Yes, and then I encourage you to join our symposium, and we consider with some discount rate. Yes, it's I think it's cheaper compared to another symposium, especially for the online presentation. And we also consider for the local student and scientists, and please submit your paper. And it's not just mainly in synthetic aperture radar. We also consider to make the the communication and sharing the knowledge with another expert in a different field. Yeah, including the optic sensor on the light noise, the trend of the IoT, and you can also make the presentation here, and we can combine with the synthetic aperture radar. Yeah. Okay, and yes, the final deadline is yes, June 30. Yeah, please remember June 30. It is in the deadline, and we don't extend again. Yes, because we need to consider a very strict schedule. Yeah, and the pre-conference we already held several series of the tutorial, and today by Professor Avik, Professor Shimada, and also Professor Steven Gao. Yes, and I hope many students and the especially in the young scientists can learn much. Yes, from the expert that explain the in the lecture today. Yeah. Okay, today the detail is like shown here, and thank you very much to Professor Avik, Professor Shimada, and Professor Steven Gao to give the lecture to all of us. Yes, I hope we can learn here much. Yes, and finally, keep healthy. Yes, and please enjoy your tutorial. Thank you very much, and I give back to Dr. Ilham. Thank you.
Please, Nisa, continue.
Okay, thank you so much. Thank you for the brief speech in opening this tutorial, Professor Josafat. Now we come to the main session. I would like to invite Dr. Ilham Alimuddin to moderate this session with the 3 speakers, including the question and answers for each speaker. Dr. Ilham, the room is now yours to handle. Thank you.
Thank you, Nisa. Thank you very much for addressing me. First of all, I would like to say Minal Aidin wal Faizin for those who audience just finished the Idul Fitr of our celebration. Yeah, and also, of course, I would like to address Professor Avik Bhattacharya, who already with us to give us his lecture today. So as I already mentioned in the beginning, Prof Bhattacharya, that my name is Ilham Alimuddin. I am now moderating this session. I'm a lecturer from Masanobu University. Okay, Professor Josephat has mentioned about our tutorial series, which is this is the last one, but hopefully there will be another one coming later before the conference, the real conference in November about Upstart 2021. Without further ado, I would like to read a little bit of CV of Professor Bhattacharya, Dr. Avik, as we probably can call him. Professor Avik Bhattacharya received his integrated Master of Science degree in mathematics from Indian Institute of Technology in 2000, and his PhD in remote sensing, especially on image processing and analysis from Telecom Paris Tech. Yeah, so graduated from French University, and also he is actively involved in Ariana Research Group in the Institute National de Research on Informatique in Sofia Antipolis, Nice in France in 2007. He is an associate professor at the Center of Studies in Resources Engineering, IITB. This is similar sound to ITB. It's an Indian Institute of Technology, Bombay, yeah, in Mumbai, India. Before joining IITB, he was a Canadian government research fellow at the Canadian Center for Remote Sensing in Ottawa. So as you can see from his CV, he's around, he's been in France, in Ottawa, in Canada. He received a Natural Sciences and Engineering Research Council of Canada. This is a prestigious visiting scientist fellowship at the Canadian National Laboratories. From 2008 to 2011, his current research interests include imaging radar polarimetry, where we will hear a lot today related to radar polarimetry, a statistical analysis of polarimetric SAR, application of radar remote sensing agriculture, cryosphere, urban, and planetary studies. Finally, Dr. Bhattacharya is the editor-in-chief of IEEE, Geoscience and Remote Sensing Letters, or GRSL. Those who involve a lot with the IEEE JRS is familiar with this journal. He is an associate editor of this Journal of Remote Sensing. He is a science partner journal. He received as an associate editor of IEEE JRSL from 2016 to 2018. In 2017, he established the IEEE GRSS chapter of Bombay section. I think this is also for Indonesian case. We also have this section, and he was a guest editor of the special issue on applied Earth observation and remote sensing in India in the IEEE Journal of Selected Topics. So that is brief, because I believe Dr. Avik or Professor Bhattacharya has a long actually list of activities in the remote sensing area, especially for this polarimetric SAR. So today we will have a very good lecture from him on his expertise. Audiences varies, Professor. There are students, lecturers, various universities in Indonesia, I believe. I cannot mention one by one, at least some of them are my students as well. They are really eager to learn more about this SAR technology, in particular the polarimetric one. Because as I always remember Professor Josephat lecture, because I happened to be his student in Chiba University last time, the advantage of these SAR images is compared to the for the optical one is because we can take pictures although it's raining in the middle of the night, and especially in the cloudy. So this is part of the advantage, and this is what I think Professor Bhattacharya later will elaborate more. I think that's all that I can just prolong for a while. Later on we will have a discussion. There's a question and answer session. So you would like to give questions, you can put it in the chat room. And there is also a Slido application that you can ask question within that. Later on after the lecture, we can choose question that can be answered by Professor Bhattacharya. I hope I pronounce your name correctly, sir.
Perfectly fine.
Perfectly fine, okay. All right then, now is your time, and I think around 40 to 45 minutes will be fine. We'll leave it a little bit minutes for some question and answer later too. Time is yours, Professor.
Sure. Thank you very much. I'll start sharing the screen. Is it visible?
Yes, yes, it's visible, and your sound is also very clear.
Okay, thank you very much. First of all, thank you very much, Professor Yosefat, for this invitation. It's a pleasure to be here. Thank you, Professor Ilham, for this nice introduction. I am really honored to be a part of it. Okay, this topic today, as you have seen, is I'll talk about information extraction from polarimetric SAR data. And before me, many renowned experts in the field have already talked about many aspects of SAR data and polarimetric SAR data. In this next 45 minutes, 50 minutes around, hopefully I can manage the time, I'll be talking about some of the recent developments which have been there in our group and along with collaborations from various parts of the world in information extraction from polarimetric SAR data. So there will be many things inside that, but I know that it will not be enough for this 50 minutes to have assimilate all this information, but I will be very happy to discuss offline with all the students and everyone who will be interested. It will be my pleasure to interact. So I go into information extraction. So in this lecture topic, I'll be talking about 4 different topics, but they are related in some way. First of all, the representation, then a unified framework. These are all very, very new concepts, and then going on into applications. All of them will be involving full polarimetric SAR data, dual polarimetric, and also compact. They can be extended to them, and I'll show you some of the examples and results which we have with all these different modalities of data sets. But before going on, let us understand, or it is very important to understand the representation of polarimetric SAR data. Most of you might know about it, but just to make a continuation of that, the representation is that you have a representation in the scattering matrix, which is relating the incident Jones vector with the scattered. So this scattered zone vector. So this is what is the starting point of the information which you have from a full polarimetric SAR data. So it describes the dependence of scattering on polarization. It depends upon various kinds of properties of the target, from shape, material, moisture, etc., and also the geometry and so on. So as you can see, this guy over here, the S matrix, which plays a very important role, and this is the starting point of all polarimetric SAR data analysis. Now, what is it? It is actually, if you see, all this is a 2x2 complex matrix. Each element over here is a complex data which has an amplitude and a phase. This is the absolute matrix which we are interested in. But you can also kind of make it a little bit more simplified, but just making it with 4 amplitude and 3 phases. So this is the starting point, but there are some assumptions which can be made regarding the monostatic case. That means you have the transmitter and the receiver at the same plane. So in monostatic condition, the off diagonal over here, as you can see, is sending an V, receiving an H, or sending a H, receiving an V can be considered to be equal under certain constraint, which is fulfilled for any kind of Earth observation or cases. So if you have this condition to be satisfied, which is true, then you can write down again this one, but in this case, you are reducing the amount of freedom to now 3 amplitude and 4 phases, because these two are similar, as we have seen over here. So this is the starting point of the representation of any full polarimetric SAR data. Now, going from here, we see the different kinds of scattering, coherent and incoherent. From here on, we will start analyzing. So coherent, as we see, are very nice way. I mean, everything is very proper, but nature is not so. We have kind of an incoherent behavior. So if the scattering is behavior from very regular targets, which you can have from urban area and so, then this S matrix, the 2x2 complex matrix, would be enough to characterize this kind of scattering. But as I said, real life or real situation is not so. So you have kind of a certain amount of randomness in the scattering. So certain amount of randomness in the polarization structure of the scattered wave. And that we call as partially polarized wave, unlike when we have completely polarized wave, if things are so nice. But when we have partially polarized wave, this S matrix is then not enough. We have to stop and think. This is not enough to characterize the mechanism. In that case, we go for a statistical description. The question is how we go for a statistical description. So it's again another way of representing full polarimetric SAR data. So I'll just go step by step. The first one, as you have seen, is S matrix, which is good for coherent target. So you have these two columns where you can see is transmitting and horizontal, receiving and horizontal, transmitting and horizontal, receiving a vertical. So this one column and two columns. So there are two columns and a 2x2 complex matrix. This representation suits well for coherent. But as I mentioned, that when we go from full to a partial polarized, so we have to go through some steps. The steps involved are we convert it into another representation, which is the scattering vector representation, which is nothing but vectorizing a matrix. I'll not go into the detail of that, but here it's just a representation. There is no increase or decrease of any information from it. From here, we go to what is called, all of you have been using a lot of a covariant structure of data. And then we go into what is called as a coherency matrix or the covariance matrix. Both of them are covariant structures. But just because we use different basis matrices because of certain reason, and that would be clarified a little bit later with the physical justification, we have two matrices. One we call as a T, the coherency matrix. Other one is called the C, the covariance matrix. But in general, but in simple mathematical term, both of them are covariance in nature. And this is nothing but a 3x3 complex matrix. These matrices have some property. They are Hermitian in nature, they're complex symmetric, and they also are positive semi-definite. So they, because of the mere construction of the data. And this is when we have incoherent target, this is the way we can represent. So there are representations in scattering matrix when it is good, when you have a representation for a coherent target, or you can have a covariance nature. But there are other representations also, which has been seldom used, but it's very, very important, is a real representation. You can have a representation by what is called the Queneau matrix after the person's name, Edward Queneau. It's a real representation. It's the same information, content is not changed, but only that it's a real information over here. It can be also in the same form when you have the covariance structure for an incoherent target. The things remain the same, but only that you have an average information. Each of the element is an averaged information. But all of them is a real representation. Each element over here is real. It belongs to R10 because since it's symmetric, you can only see the diagonal and the upper part of it. So it's a symmetric matrix where you have. So this is what are the representations. But the point is, are they related? And yes, there is a simple way in which all of them can be related by simple transformation. So you can see all of them are related in some way or the other. So if you can go from T to C, C to K by this simple transformation, you can go from S to all of them. But as you can see, there is a dotted line with red saying that once you have a covariant structure or an ensemble average quantity, you cannot go to an S which has a rank 1 matrix. So it's not possible to go back to an S matrix. But in other ways, you can go back to each one of them by simple. So this represents all of the representation of full polarimetric SAR. Now, moving from here, target characterization. So what is the idea is that you have the representation, but now you want to break it up into constituents in which each of these constituents have some physical meaning. That's what we would like to do. Because when you have the measurement, you have either this one is an ensemble quantity, an average quantity, but the idea is that to break it up in a decomposed them in each one of them. So in literature, there are many conventional settings. These are very, very widely used, very popular, and has been exceptionally given good results. One is in the model-based decomposition started by Dr. Freeman and Durden. Then it has been developed quite extensively by Professor Yamaguchi and others. And people have followed different versions of it and also extended in different directions. These are very, very widely used, and I'm sure most of you have used it. It's a model-based decomposition. The other school of thought, the other one is the eigenvalue eigenvector decomposition, It's a mathematical abstract, like unlike the model-based where this is a physical construct. And there has been decompositions which has also been done by Dr. Cloud and Potier and also Dr. Vidatu. And I call them as a conventional setting. This is already there and been extensively used. I go to these one which are newly developed, and I call them as non-conventional. Why non-conventional? I will come back to that. So we come back to the first one, which is a scattering power factorization. Please pay attention to the word over here, factorization, unlike what we call over here as decomposition. So the idea over here is based on a very simple fact, which comes from the geometrical analysis of pulsar data, where we try to find out distances within the manifold in which these matrices lie. Here, they are real matrices. Over here, as I said, I will be utilizing the Kano matrix, as you have seen before, the real representation. And if you just see, it's a very simple way to find out the geodesic distance between these two matrices. So this is nothing but a part of the greater circle. You can say this is a sphere. You can think of it to be a unit sphere in a very higher dimension of 15 dimension. That's because it can be reduced to a 10 dimension also. But this is what it gives. This gives you an information about the distances between the matrices. And you can just normalize them between 0 and 1. This is what we'll be utilizing subsequently. And you can see there are papers which has talked about this in several applications. I will go to them slowly one by one. So with this unified framework, what we call as a unified framework, we will talk about some descriptors, which are descriptors for analyzing target. I will come back to this factorization, power factorization, unlike the decomposition which we mentioned, and then we'll go and see some of the Earth observations. So the first one is a roll invariant scattering type parameter, which is already given in literature by Dr. Cloud, Potier, and Rida, is that this characterizes the scattering mechanism of a target. It's something very simple as that. We find out the geodesic distance between the observed Kenyu matrix and a Kenyu matrix corresponds to a trihedral. And I give you a list of them. You don't have to memorize them, but this is already there in literature that you can take different targets, starting from trihedral to dihedral and so many of them. And it can put them in a matrix representation. These are simple and available in literature. But what we have is, if we utilize these matrices and see this quantity, you'll be able to see that this quantity actually characterizes different angular behavior, and this gives information about the scattering type. If this is a trihedral type, which is something like a surface time of scattering, this is 0, this quantity. But on the other extreme, if it is a dihedral scattering type or even bounds, then it is another extreme, which is 9. So the scale is a continuous scale between 0 and 9. But there are two other targets over here, which are the helix. These are asymmetric kind of target. So you can see that there is a problem over here because there is an ambiguity which always lies over here. So if you have in a resolution cell, either a dihedral or something like an asymmetric target, which is a helix over here, you won't be able to distinguish. And this is a drawback. So in order to avoid this, so this is a target which looks like, this is the area of where I come from, Mumbai. This is an ALOS2 image. Thanks to JAXA for sharing this image. You can see this is the ALOS2 image. This is Mumbai, the area, it's a metropolitan city. This is what you have. You can characterize this target, which is a water body, to be very, very low. Urban area, very densely covered urban area is towards that 90. In between, you have forest and so on, agriculture, where it is in somewhere in between. So this gives you information about from an odd to an even bound scattering mechanism, which is characterized with this scattering type parameter. But the idea again is that the helicity parameter. This is a parameter again which characterizes the asymmetric nature of the target. So again, the same thing I wrote over here, but concentrate on the last two rows, which are the helix. Now, if I see this parameter, I can see that for this, it is 0 again for a trihedral, which is obviously true because this is a symmetric target, and dihedral is some value. But now you see we are able to discriminate between these, which we failed utilizing the alpha GT parameter. That means along with the alpha GT, we would require this parameter for an unambiguous characterization of target. So these two parameters now gives a polarimetric descriptor. What else can we do? This is what it looks like. Of course, the range is very low, the dynamic range, because you get less amount of asymmetric target. Only in the urban area you would get some. So the range is very low, but you can see still you are able to see some of the differences where you would mix up if you only use the alpha, which is the target only scattering type. This is symmetric, asymmetric, the two extreme ends. But other thing also you can characterize is something amount of purity. How much pure is the scattering? That is also a very important parameter. And it comes with the same thing over here, the geodesic distance between the observed Kenyu matrix, and a Kenyu matrix corresponds to a perfect depolarizer. Of course, a perfect depolarizer you can never get in nature. It's an abstract, a theoretical abstract, which is something like this. That means any polarized wave going through this kind of a target will be completely unpolarized, which never happens because it's always partially polarized. But you can take this to be one extreme case. And with this, you can consider them to that if this quantity, PGD, is 0, this is an ideal depolarizer. But if it is 1, then it is for coherent time. So this gives you information about the target being completely coherent, or it is totally a depolarizer. An image will clarify that. Same image I take. Now you see, if it's a water body over here, it's a calm water body. This is the Arabian Sea. So if you see that the scattering over here is, as you have seen, it is a surface-like scattering, but it is also very pure in nature, high amount of purity. But if you see over here, which is mixed up in the resolution cell, scattering from different kinds of target, you see the scattering purities on the lower side. Of course, it's not, of course, equal to 0, which is, as I say, not possible, but towards the lower side. So this gives an information about the amount or the amount of purity in the scattering. So you have seen, it gives you the information about scattering type, it gives you information about the scattering asymmetry, and it gives you the information about the scattering purity. So these are the 3 parameters which have been generated utilizing only a notion of a geodesic distance between an observed Kenyu matrix from a resolution cell, from a pixel, and again these targets which are there in literature. So going from here, next is how do I go into power factorization? As you have seen that there are decomposition methods, as we have mentioned, there are a number of them, and it has been very popular. But we will talk about factorization utilizing n different scattering models. So what is the idea is that? The idea is to separate the span. So you have the span, which is the total power. So what is the idea? How do you break up that span? So you want to break up those span, the total power, into different constituent elemental power. So the idea is that, how do I do that? It might look a bit complicated, but believe me, it's simple and simple way of doing. The idea is that I find out the dominant scattering I take it from different targets, the geodesic distance, and I can find out what is the kth dominant target, which is nothing but 1 minus a geodesic distance. Geodesic distance is a distance. It tells you about dissimilarity. 1 minus dissimilarity gives you similarity. So 1 minus this one gives you similarity to the target, kth model. You can take any model. Now, what is the dissimilarity? The dissimilarity is with the other target. So once you have the similarity, you can always go to the other k minus 1 dissimilarity. You form the product of that. So it is nothing but the product of that multiplied with the similarity. And then what you do, you just take a sum of them from 1 to all the targets. So it's actually a straightforward, one line to do that. So this gives you the characteristic. But the point always is that how many ever targets you bring, you will always be having a residue component, because everything in nature you cannot fit in completely. So I have an information from a pixel. Now the idea what you are doing, you are trying to fit in different models over here. How many can you bring? 10, 20, I don't know, many of them, but still you will be left out with something which you cannot fit. So there will be always a residue component. And the residue component is what is left from here, is the product of the other which has been left. So if you can see, it's nothing but actually what I call as a factorization. Unlike the decomposition where you break it up into this A plus B plus C and so on, here you are doing it as a factorize. So it's a multiplication, but what you are taking into account is the notion of dominance that you can always do. And this is also can be related to what has been given by Professor Heinen in his 1970 PhD thesis, which is, of course, a very big starting point of SAR polarimetry. It actually can be related to an equivalent of the total power breaking up into different constituents element over here plus a residue. So I call it as an equivalent of iterative Heinen process. So maybe if you are not familiar with Heinen, you can have its wonderful work, and it has been followed by many. This is almost a similar equivalent thing, and this gives you information about factorization with n components. And then we can see different ways in which we can do it. We can do it for coherent target, but also for incoherent target. So I do it for coherent target. This is again analogous to image of ships. You can see that what is the first dominant scattering mechanism is something is a dihedral and a narrow dihedral, which is true. Second dominant, if you go, it goes to helix, the target. And then after that, from third onwards, it can go to a little bit of noise. But you can always find what is the dominant mechanism actually over here. If you go to incoherent, then you can take the same image. This is the radar set 2. So you can say the first dominant over here is narrow dihedral, but also some dihedral, which is also true. The surface over here is a trihedral, which is also known from literature. But as you can see that it is, if you go from the second dominant to the other mechanisms, it goes on to be noisy. So if you go to the different mechanism, so with utilizing them, I can find out this is analogous to image of Mumbai area. And if I try to see that this is the dominancy map, and the first dominant over here is even bounds. I have the odd bounds over here from the water body and some of the volume scattering from the vegetation, which actually correspond the same as you would have from a model-based composition. I mean, the way the mechanisms are, it actually follows the same. But if I utilize again the power component, this is how the power component looks like in terms of, again, the three component, the dihedral, the surface, and the volume. You can see the urban area looks quite a mixture, of course, dihedral and some surface, so it's not red as such, but pinkish. But over here, you can see this is urban, this is an area which is the forested area, which is green, which is the volume and everything. So it actually mimic the same thing as you would have got from any other decomposition, but the total way of understanding is from a factorization frame. Now, utilizing this mechanism of this simple fact of a geodesic distance between measurements and between models, we have given many different novel descriptors for snow cover, urban, and so on. So I'll just give you examples of each one of them. So if I go for snow cover, you can see that it can be utilized very, very nicely for snow cover mapping. I have this area which is from the Himalayan region. Many of you know about it. This is the Himalayan region. The image taken by radar set 2 in February and in August. One is snow cover, one is almost snow free, snow has melted. If I use a full polarimetric SAR data, and I use this geodesic distance and do a threshold, I'm able to capture nicely the snow cover area. So binary, snow cover and non-snow cover. But if I take this full polarimetric data and I convert it, I just take only some information from it, which is nothing but the dual copolarimetric, HH and HV. I take the HH, HV and the VVVH, so that means not the full polarimetric information, but some portion of it. I degrade the result, but you are still able to quantify to a certain extent. But this is utilizing the same information about geodesic distance between targets. Urban area, we can also quantify urban area changes. This is from an area of Los Angeles, 2009, 2015, same area, finally co-registered. This is from an UAV SAR data, very high resolution, L-band data. You can see over here, the urban area is not present. It is again urbanized. You can see that the changes which can be seen with a dihedral type of scattering is very, very prominent. That means I just need to find out a similarity measure between the measured Kano matrix pixel-wise from 2015-2000 and a dihedral over here. So dihedral is Why dihedral? Because dihedral is a prototype of scattering mechanism from urban area. And if you can utilize them, I'm able to see the difference is quite evident and from here. Clustering. There are clusterings of method available in literature, and this is what has been there in literature, which has been done by the Freeman, Durd, and decomposition powers and utilizing them Wishart type of a classification. It has been done by Professor Lee and others. This is what you have as the unsupervised way of clustering this area. And in terms of odd bounds, volume, and double bounds, each one of them having 5 classes of each. And this is our way of doing it. We are replacing the Freeman, Durd, and over here with our type of power, which I've just shown a few slides back using the geodesic distance. So if you replace that with this one, with a simple clustering method, which is available to keep this Wishart, you can see it's better than this. But just to appreciate it, I will just zoom into an area to see that this area, which is an urban area with Freeman, Durd, and Wishart, it is not able to capture quite a few of them. Here it is better than before utilizing our method. So what we have done is we have just done a clustering method utilizing this geodesic based powers, which we have seen a few slides back, and utilizing a Wishart. Wishart remains common for both of them. I can always also do something which has been you have been doing reading in polarimetric literature, which has been quite successfully done, which is called the H alpha segmentation, the entropy scattering angle given by Professor Cloud and here. You can we have made another one which is called the PGD and the alpha GD, which is the purity parameter, which runs from 0 to 1. 1 is highly pure, 0 is totally non-pure, depolarized, ideal, and alpha GD gives a scattering. So if I just draw them on a 2D plane, simple 2D plane, and this curve, everything has a mathematical relationship. And if I just make some of these clusters, which has come from some physics of scattering, then you can see that I am able to properly cluster this image unsupervised way like this, which tells me that I have 8 clusters. And these clusters, of course, corresponds to the urban area, which is very true. This is totally an urban area over here. So, and this one corresponds to this 1 or 2 clusters, which is something like a water body, and others also has different clusters. So without having any a priori information, I can take this image and I can put this into a clustering framework, and I'm able to get this cluster of 8 clustering. So simple segmentation. Radar built-up index. So how do you characterize the amount of built-up area? This is very new. There have been no such index given for radar images. There has been some indices which people have used for optical remote sensing data sets, but not for full polarimetric. This is what we have used. So this is an area, the same area, radar set 2 over San Francisco, and utilizing our methodology, we can find out the built-up scattering dominance. The same. So you can see that the dominance is, of course, in the urban area, which is clearly very evident. But only now we have different classes of dominancy, first dominance, second dominance, and so on. And beyond 3, we don't see anything because it is not coming anywhere. So we have taken the dominancy information, and we are able to see that they have the dominancy, which comes from an urban area, is actually able to characterize it better. And on that, you can have this is the radar built-up index. This is a very simple way of finding out. You can see on this paper. This is the radar built-up. See, you can see roughly you can see with a one quick look that everything above 0.5 is corresponding to an urban area. Everything below that is non-urban area. So you can do a simple thresholding above 0.5 or less than 0.5, or you can use any other simple thresholding method which are available in image processing methodology. And you can see that when we do that, we get something like that. It's just with a simple method of one method, another method, another threshold method with the index. You can see that I'm able to capture quite well the total urban area. Again, the logic behind it is, again, I am utilizing the same geodesic distance between the measurement and targets. With that, I'm able to characterize the scattering type, the purity, the helicity, and we are also able to utilize in a different framework the scattering powers factorization, not the decomposition. I'm telling you again, it's factorization. And with that, we can get any number of power components as you want, as many as targets you can think of. So with that, also we have found out different mechanisms to find out urban areas. And I can give you some example. This is an UAVSAR image of L-band. You can see it's nicely captured this area, which is so this is again for urban area. I go to a different application, which is very, very important for us, is radar vegetation index. There has been some indices in the literature, which is called the radar vegetation index in literature, but this is not, so it has been used a lot, but we would try to look into different ways. Of course, I'll go quickly to look into what is called as the generalized radar vegetation index. So the idea is the simple again, that we construct a Gannon matrix, which is the measurement. But from there, we find out something which is called as the generalized radar vegetation index, which gives an information about from 0 to 1, characterizing if there is vegetation or not. So this is again utilizing the geodesic distance between the observed and the elemental target. And this has been successfully applied for many different areas and very different types of crops. You can see that how you can see the temporal growth of this parameter for a field which is our area in Canada. These are different fields constituting different kinds of crops. As you can see, the temporal evolution as the phenology increases. You will appreciate it more when you see this small movie which talks about how this grows, this information which can be characterized with the growth of the season. So this characterizes the amount of vegetation area. It starts from being very low. If you can see, this is very low over here in blue. So there is nothing over there, no vegetation. As vegetation phenology increases, there is an increase in this quantity. We have seen it over rice, which is very, very important for our area. We can see that this is the growth of rice on a temporal series. And this is the RVI, which is there in literature, the radar vegetation index. But this has, so if you see that for many cases, it fails to characterize, even though the rice has been grown over here, almost to a large extent, it is unable to capture the information over here. But with this new parameter, you're able to do that. Things become much drastic when you see that the fully grown rice paddy over here, you are unable to characterize it over here. It still is unable to give you information with this RPI. But with this new product, we are able to see that the growth is quite nicely picked up over here with a high value of GRPI. And this we have utilized to do some estimation of a retrieval of biophysical parameter, and we can see that it performs much better than the RVI, the radar vegetation index, which has been given in literature quite some time back. And we have, with ours, we are able to characterize much better. If you see the same thing, how the behavior is when the rice is not sown, so there is no, so you can see that the alpha, the scattering mechanism is quite different from when you have rice fully grown. So it's able to characterize rice. If you see the purity parameter, when nothing was there, the scattering was pure. When the rice has grown, fully grown, you can see that the purity has decreased because the amount of randomness in the scattering has increased. If I use the segmentation, utilizing again the same thing as I showed before, the alpha and the purity, you can see that here you get less classes. Only over here you can get the urban area. This is the urban area of Vijayawada. This is the city in the south of India. But here, if you can see, when the rice is fully grown, you're able to get these clusters to be corresponding to rice. If you see the powers again, you can see that this is corresponding to more power over here. It is over here. You can see it corresponds to the power which is coming from the double bound scattering from the rice. So this gives you an information about all of this, which has been characterized with a single information characterizing the geodesic distance between different kinds of mechanism, and that has been utilized for all different applications. From here, I go to the next one, short one, which is, I call them as a model-free decomposition as opposed to model-based over here, but this is only in terms of decomposition. So this is a very, very new development of model-free decomposition, again in the non-conventional setting. So the idea is what, as you have seen from previous lectures, I will not go into detail over here, that you have the T matrix and you are trying to decompose them into several constituent components over here. So going from surface, dihedral, volume, helix, and so on and so forth. And there have been a lot of literature which has been there, and literature has been coming quite often over here. There are issues over here, is the information utilization, negative power, inversion priority, and so on. And there is plethora of models which has been there in literature. So this has already been an established field and has been doing well and is being widely used. We go from here to another a direction. So another unique way out, I call them, is what? Is that I take the elements of the coherency matrix and I take this information, which is called as the Barakat degree of polarization, given by Barakat in 70s. It has been rarely used in the domain of full polarimetry. It gives you an information about a quantity, about a polarization, the amount of polarization. And this is called the Barakat degree of polarization, not unlike the conventional degree of polarization, which is used mostly in ellipsometry. From there, I utilize the scattering power type and I get the scattering powers. This is what very simple way. But what is the benefit? It's model free. So it is unique because you don't have to bother with any kind of model. So you don't that if you change the model, your things change. This is unique. There is scattering type power simultaneously. So it can find out there is no hierarchy or criteria in going from branching condition. There is no negative power. You can equivalently go to other modality from full to compact to dual copolarimetric and maybe bistatic. This has been still under work research, but up to here it has been all done and published. And all these parameters, all these power parameters are rollable. You can see how. So let's say I have this matrix as a full polarimetric matrix. From here, I just get these two components. These two components are nothing but the two elements of the Kano matrix, the first one and the 441. This is simple. It's very much available in literature, nothing new. But if I go to also compact data, which is now, there are many missions which are coming up. The RCM, the Radar Search Constellation mission of the Canadian Space Agency, will give data in compact mode. The compact mode will give you a 2x2 complex matrix. You can go from there to the Kano matrix, which looks something slightly different than this one. So I can utilize this Kano matrix and form this parameter, which is called as a scattering type parameter. Similar parameter as has been given by Dr. Cloud and also by Dr. Rida. They also call it as a scattering type parameter. To have the similar name, I give a scattering type parameter. It characterizes similarly as the parameter type, varies from -45 to 45. -45 gives you complete dihedral, plus 45 gives you complete trihedral. So it goes from the two extreme from a trihedral to dihedral. Utilizing this parameter and what is called as the Barakat degree of polarization. This expression is, you can see it is where you have n to be the size of the matrix. So I utilize this parameter over here, this mm, and with this I find out these three components, which is nothing but the power in the surface, the power in the dihedral, the power in the volume. So the volume is volume power in literature has been associated with a model, a volume model. But here, as I said, it is non-model. This power volume is actually nothing but the amount of depolarized power. So this is a depolarized power, but to have the same convention, I write PV. But there is no volume model attached to it because this is totally a non-model based. So this is the diffused power or depolarized power, and these two corresponds to the surface and the dihedral. This corresponds to a 3 component. We have gone one step more to go to a very newly published work, which is the 4 component. What we have introduced is nothing but an helical power also over here. So this is again the same way, but you can have the helicity power as something like this. The K14 parameter, the modulus of that is nothing, but as you can see, it's the imaginary part of K23, which is nothing but simple as that is the model for helix. So if you can utilize them and see that we have these powers, the helix power and all the other powers are similar to the other. But we compute first the PC power, the helix power, then the volume power, add both of them and subtract from the total power. So you get a residue power. So the residue is the polarized power. On this polarized power, I find out these two even and odd bounds and the even bound. This has been also published. You can have a look at them. Again, you can see this is one step to go from the T matrix to all the powers. There is no branch. How it looks like, this looks like something like this. Again, similar to as you have seen before, the scattering type mechanism from theta FP, which corresponds to minus 45 to 45. Is 45 is trihedral, this is dihedral.
Yes.
This is corresponding to the scattering powers. You can see this is from the Professor Yamaguchi's decomposition of the original of the rotated one by coherency matrix. This is how we get the 3-component decomposition also from this. And we have also done some segmentation utilizing the power component, but I'll not go into the detail of that. You can find it in the paper. There are some also radiation index which have been done for the dual pole and the compact. There's similar ideas, but has been extended to dual polarimetric data. And dual polarimetric data is nothing but a projection of the S matrix. You can see that the projection of the S matrix onto a 1,0 component, which you have the HHHV, or a 0,1, which you get a VVH. And utilizing them, we have utilized them in a C2 matrix, and we have gone utilizing them in terms of the degree of polarization. And this is what you have as the dual polarimetric radar radiation index. So before you have seen the full polarimetric radar radiation index, this is something new as what is called from the dual polarimetric radar radiation index. You can have them for dual polarimetric SAR data. So for Sentinel-1 type of data. So if you can see there, it corresponds very nicely to some area on a 2D plane where you can see it goes from where you have no vegetation, bare soil to vegetation. You can see them the smooth transition from them. I'll just show some examples of them. This is an example showing how with different crops, you are able to see the changes of the dual polarimetric vegetation index. And also we have compared it with the full polarimetric vegetation index also, just to see that if you have a full polarimetric data and you have a dual polarimetric data, how the variation. Now the variations are nicely captured by the dual polarimetric data set also. And that means that we will be able to find out very nicely the characteristics of the vegetation. If you see in the 2D plot, you can see the nice transition when you have from a bare to a vegetation. This point over here, the cluster transition from 13 June to 31st July, when you have the crop phenological changes happening, can be nicely characterized within this kind of a polar plane. We are able to do that with a correlation analysis with different targets, with different biophysical parameters, and they perform very, very well compared to what is there in the literature. We go to the compact case. Again, compact as dual is nothing but again a projection of the S matrix, but in a different way. It is projection with the 1 plus minus I, where you have a combination of the HH and the HV together. You again can form the C2 matrix in a simple way. These are all similar way as you can form, but you can also relate it with the Stokes parameter. If you utilize them, then again, as you can see that this, before it was a DPRVI, now it is a compact CPRVI. It's the same, there is no change at all. Only the change is in the fraction because of certain physical limitations of the compact polarimetric. But I would like to go quickly to the results, and you can see that the results for an area which you have over here for soybean, you can see that it again captures very nicely the changes in the phenological structure with this. This is utilizing compact polarimetric circuit. So what did we see that we have this radar vegetation index, which is a very, very important parameter for agricultural application. We have it for full polarimetric SAR data, and we also have equivalently for dual polarimetric SAR data and also for compact polarimetric SAR data. And these are almost equivalent formulation. Slightly, little bit changes in the equation because of the limitations which have been taken to be account, but you can get all of this in the paper. You can see the detail. So here we are again able to characterize the correlation with the biophysical parameters. So you can see that the PI, the plant area index, the vegetation water content, and so on, they are nicely captured for different crops, for wheat and soybean and so on. So that means this parameter could be very much utilized for agricultural application. We have done some analysis for estimation, inversion, and it very much nicely follows with the PI estimation and the PWC and so on. So these parameters, as we have seen, the radar vegetation indices for the RVI, the GRVI, we call it as the generalized radar vegetation index, corresponds to full polarimetric SAR data. We have the DPRVI, which is nothing but the dual polarimetric radar vegetation index, and the compact one. They can be used for application in agriculture. And we have utilized them all. They have been thoroughly studied over different geographical areas and for different crop types also. And we have been utilizing it for many other different areas. Now from here, we go to the end of almost the end of the presentation to say what next. Next, as we know, there'll be so many of data coming in full polarimetric, dual polarimetric, and compact. You will have the ALOS-4. There'll be Sentinel 1A, 1B is there. You'll have the 1C, 1D. There'll be the ROSE L, which is also called Sentinel 12, and the Sentinel 1, the next generation NG. There'll be the NISAR, which is the NASA and the ISRO, the Indian Space Agency Cooperation Mission, which will have L-band and an S-band data set. RadarSat Constellation mission is already there, up and running. You have the compact data set. So this is, and there will be many more to come. This is only a few of them over here. There will be many, many more to come. This is what is coming. But there will be so much of data to handle. As you can see, there will be data which will be increasing in the repeativity, timing, in terms of the information content, in terms of, so the volume of data will be increasing a lot. So maybe utilizing them in a single machine, which is your own machine, would be quite difficult and tedious to do. So slowly we are moving into cloud-based computing. So we are moving into Google Earth Engine or the Microsoft Azure, Amazon, and so on. There'll be something which is called as the MAP, which is from ESA, the European Space Agency, which will have all the methodologies. We'll be slowly putting up. It's just started. We'll be having for the biomass mission and extended it for other missions also. And we will have the data sets and also some of the modules to use those data sets. So the idea is that of all these sensors and all the data sets will be large and huge in terms of quantity, quality, everything. So maybe it's time to now move into a cloud-based platform where you will be able to do that. And in that regard, we have already started our journey. So we have done some new dual polarimetric GRD product. As you know, the Sentinel-1 also have this GRD product, the ground range detected product, which you can get on the cloud of using Google Earth Engine. And this is only the two channels you have, the intensity channel in decibel. You have the VV and the VH. So this is the GRD product which you have, but this can be utilized on the cloud. So very recently, this paper is already there out. Recently, we have done some studies and we have given some parameters which are equivalent in terms of the scattering type parameter, the entropy, and the purity parameter for this kind of data sets, and we have utilized them for agricultural application. As you can see, the small movie snippet over here, is that these new parameters, how it varies over agricultural area for the change on the phenology for the day of the year. So you can see that it is able to capture the changes very well, this new set of parameters. So that means with this, we can go ahead and try to find out that if we have only the GRD product, because always it will not be possible to get the SLC product. Of course, Sentinel-1 have the SLC product, but it's very heavy to work with them on a machine, on a local machine. So this is all of these are done on the cloud. So this is where we are heading to. And also, I would say the polarimetric SAR community is also heading to, is to utilize them on a larger scale on having for different kinds of applications. And just to tell you that whatever I have shown, most of them, almost most of them are available with what is called as a Pulsar tools. So I'll be very happy to, and this is nothing but this is a QGIS plugin. It is very, very simple to use. You can have them. It is available as a QGIS plugin. If you have any questions, anything, any concern, please do write to me. I will be able to make you contact with the people who are managing it. It is from our lab itself. All of them are available. All the techniques and everything are available, and it's very, very easy to use. So if you want to use them, please feel free to use, and we'll be happy to answer any queries or any suggestions you might have to improve it or include many other tools if you would need. This is already there available. So last of all, I would like to thank my collaborators who have been always there helpful in all this work, and there are many who will be on board soon for many other work. Wow. There are many books available in the literature. You can go through them. I'm sure you have already seen them, and I think Professor Yamaguchi's book is also over there. It's a wonderful inclusion in the literature of SAR polarimetrics is also over there. With this, I conclude. Thank you very much. I think I'm on time. Thank you.
Yes, basically you spent right on time because we move a little bit 4 minutes later. So that's great timing, Professor Bhattacharya.
Thank you very
now,
much.
We can have a little session of questions. I know this topic is quite heavy for maybe some of our audiences because SAR itself is something that not many people still can cover. And not to mention now we move to the polarimetric, not to mention the dual polarimetric, interferometry, and other stuffs that related to SAR coverage. So I believe the audiences still have a lot of questions actually related to simple SAR and also about the polarimetric. In the Slido, where we have questions in here, if you can stop your sharing, but I can read actually, no problem. Audience also, when you write down the chat or on the Slido application, please write down your name so then I can mention who is asking questions. So Professor Bhattacharya, there is a question here. Unfortunately, he didn't write his name. What is the free software to process Pulsar? You did mention this, that Pulsar in tools, but there might be any others. Is there any workshop for Pulsar? And what is the difference with Pol-InSAR? So this is probably a combination with the polarimetric and interferometric SAR. You might want to elaborate this a little bit. So
right,
please.
Thank you.
Yes.
Thank you very much. Yes, the most popular, the most used software which you can get is the Pulsar Pro software. As you know that the Pol-InSAR conference, which is organized by ESA, has been recently concluded. I think that was a week and a week two ago, which was a 1 week online event, unfortunately. But over there, they have released the recent version of the Pulsar Pro software. You can find it on the link of ESA. If you don't find it, please do write to me. I'll be very happy to share that. This is the recent version of the Pulsar Pro software. Most of the images, polarimetric SAR images, I mean, now it is almost all of them could be read over there. There are many modules, which can be utilized over there. This has been there for long, and with Professor Eric Potier from the University of Rennes in France, this has now been one of the most utilized software in the domain of polarimetric images. They also have other modules for PolInSAR also. The other one which you can use is the ESA software, which is the Snap. Snap is also Snap also has many functionalities for polarimetric. They are increasing a lot more of them. I think the recent version will come soon, which will have more functionalities. But at the moment, also they have a lot of functionalities out there, and you can use the Snap also. It is very useful. So at the moment, PolSAR Pro, the new version. And the Snap is the one which can be utilized for all your applications of full polarimetric SAR data and also dual polarimetric SAR data. So this, I think, so if you have any issues with downloading of PolSAR Pro or any other things which you want, you may please drop in an email. I'll be very happy to help you. The QGIS plugin which we have shown, because now PolSAR Pro will also have a QGIS plugin. This is very new, and it's very useful now. So keeping in mind that, we also made this also, as you have seen, which is called the PolSAR tools. There have some functionalities which is the newly developed methodologies from our lab with all different collaborations. This is also a QGIS plugin, and it works for kind of many data sets. At least it works for radar set 2, ALOS, and other full polarimetric SAR data. You can utilize that, but these are all the new techniques which are not available otherwise in any other software. But you can utilize them and see if you would like to have any discussion with us. We'll be very happy to have one-to-one discussion at some other time. And this is what is available in the community. As the next question, as you say, is PolInSAR. So this is another technology, as Dr. Ilham has have given you the answer to that. It's a combination of polarimetric and interferometric. To make things very simple, it is something that polarimetric gives you the scattering mechanism information, whereas interferometric gives you the height information, deformation. So here you are combining both of them together. So it's a newer technology where you are trying to get the scattering information along with the height information. So it's on a Z direction also. So it's more involved. So what you have is you take two instances of full polarimetric SAR data, and what you have is the combination of that information. So at the end, when you have the information, it comes as a polarimetric and an interferometric information together. What you can extract from there is that what is the type of scattering mechanism corresponding to a certain height. So that gives you the information about PolInSAR. It's a wonderful technology, and I'm sure there will be, with the biomass mission, you will have more data sets where you can utilize PolInSAR data sets for more applications.
And in terms of application, probably this would be the last one to elaborate, is the application, because in your presentation, you are more emphasizing on the use in urban changes, in agricultural crops, etc. There is a question related to the aquapond in the slide, though. You might want to mention this. And for me, how would this be useful also for disaster mapping, for example? If we can combine this polaric and interferometric, that would be very excellent for looking at the differences of surfaces, for example. But you might want to comment on other application for
that is thank you very much. That's a wonderful question. That's for disaster. It is always very important to have this kind of information, and of course this information is also very fast to be utilized for actually the management purposes. So when we can of course go into, as you mentioned, PolInSAR, but there is kind of a limitations of data sets to available where you can actually do these PolInSAR applications, and of course you can do it on a particular area as a demonstration of a methodology. But if you would like to have them on a live application kind of thing, or you want to have it a very fast, so it is always useful to have this Sentinel kind of a dual polarimetric SAR data, where you can utilize some parameters which I have shown in my lectures. You can utilize them to see different kind of changes what you can have. So for example, you have an urban area where you would assume that the scattering will be more coherent in nature. Once it is destroyed, this coherent mechanism kind of thing has been changed to something which is more randomized in nature. So this kind of what I have mentioned in some of these parameters can capture that. So you can see that there will be an instant change from a coherent nature to something which is a randomized kind of case. So these changes can be attributed. It may not be always foolproof, but this can be as a first-hand information. But now, if you want to again utilize full polarimetric SAR data, you can go for the different decompositions which are available in literature, or the decomposition which I have mentioned, the newly one, which can give you information in terms of the powers, because that will also highlight the change of the different scattering, where you can relate it to it being that it is coming from an urban, or it is an area which was before an urban, but it is not now. So that kind of change could be characterized to a disaster. And if you see the literature, there are many studies where decomposition powers has been used to characterize the changes which are happening over the same area, but at different instance of time, utilizing full polarimetric SAR data. So, but the thing is that the scenario of, as you mentioned, the scenario of SAR is changing so rapidly with the advances of newer generation of technology of SAR. But if you go to in another domain, for example, you will see that there are SAR data which are very high resolution data, but single channel. But they could be also utilized for rapid assessment. So if you would like to say very fast that there is a change or not, this could be utilized. If you would like to get more precise, then you would rely on a dual polarimetric or a full polarimetric. But the thing is, then how you would want it to do that? You would want it to do it on a rapid basis, actually, for the management of disaster, or you would like to see whether your methodology works on a certain cases. So
on the validation,
on the validation kind of cases, So these are kind of, but it's a fast changing, rapidly changing environment, and many sensors are upcoming, and it will be an interesting time ahead to look into all of them.
Right. Okay, Professor Bhattacharya, unfortunately, we are limited by time.
Thank you very much.
I believe understanding this polarimetric need more, timing, etc. But those who like to contact Professor Bhattacharya to learn more on the pulsar and polarimetric, and especially the tools, you're welcome to contact. We will give you the emails, and the presentation later will be shared to the audiences. Again, thank you very much, Professor Bhattacharya. Unfortunately, we are not having a longer time. Professor Shimada is already here for our second speaker. Yeah, we would like to welcome Professor Masanobu Shimada.
Thank you very much.
Yes, and that would conclude the session with Professor Avik Bhattacharya. Thank you very much, sir, for your lesson, for your lecture to all of us. Thank you.
Thank you very much. It's an honor. Thank you.
Yes, thank you, sir.
We
move on to our, yes, Prof. Josephat would like to say something, please, sir.
No, yes, just to say thank you very much. Yes, to Professor.
Thank you, Professor Josephat. That was a pleasure. That was a pleasure for me. Thank you.
Keep healthy with your family. Yeah.
Thank you. You too. Take care.
Yeah. Please take care there in Mumbai, sir.
Thank you. Thank you very much. You all take care.
All right. And don't forget to send us your presentation material.
Sure. I'll send it by today evening. Thank you very much.
Yes. Thank you, sir.
Okay.
Okay, ladies and gentlemen, we will move on to our second speaker, our second presenter, who happened to be with us now. Welcome. I always call him Shimada Sensei. I personally have met him before when I was at Chiba University and Professor Josephat Remote Sensing Laboratory. So just before he will give us his lecture, allow me to read a little bit of his background. Yes, this is Professor Shimada's CV, a little bit, just brief. Shimada Sensei received his bachelor award and master degree in aeronautical engineering from Kyoto University in 1977 and 79, and his PhD degree in electrical engineering from University of Tokyo in 1999. He joined JAXA in 1979. It was quite a long time ago, and conducted the research project for nearly 34 years. Yeah. His most impacted achievement are the deformation detection of the Hanshin Awaji earthquake using JERS-1 SAR interferometry. I happen to use this data as well, JERS-1, in my dissertation for the use of disaster. Generation of world first global SAR mosaics that depicts the annual deforestation change, and experimental near real-time deforestation monitoring using the ALOS pulsar ScanSAR. And he is now the IEEE fellow from 2011. I believe it's until now. I remember he received an award also from IEEE. Since April 2015, he is no longer with JAXA. He is now a professor at Tokyo Denki University and a guest professor at Yamaguchi University. And from all these experiences with remote sensing, it's good for the students to learn, and he's teaching for this radar remote sensing, focus more on the microwave remote sensing. That's the brief biography of Professor Masanobu Shimada. As I refer to Shimada Sensei, just to remind him how I use his Sigma SAR Sensei. Sigma SAR still developed. That's probably my questions later. Okay then, Professor Shimada will be talking about the SAR interferometry, the basics and application. So from Professor Bhattacharya, we already listened to polarimetric SAR. Now let's learn the basic and the application of SAR interferometry. This is one of the application of SAR data. Ja, dozo sensei, time is yours. Yoroshiku onegai shimasu.
どういたしまして。
はい。
Thank you very much. Very nice introduction. I'm happy to join this tutorial session. And my talk is SAR interferometry basics and applications. And may I share my PowerPoint? Here. This.
Right.
So can you see my screen?
Yes, the sound is clear. The PowerPoint is also clear. Carry on. Yes, continue.
Okay. Thank you very much for giving me the chance to make a presentation about SAR interferometry and application. And the product to be seen in my presentation is produced by Sigma SAR as well. And my talk contents is, let me see. So this is some introduction and exactly the same by the introduction, and the hobby is music. And okay, the contents of my talk is background, SAR and interferometry, DIN-SAR, zero baseline interferometry, 3D decomposition, time series analysis, ionosphere and troposphere, and summary. All are, I think, prepared for the basic introduction or understanding of how the SAR interferometry is prepared for some information of the Earth. And background is that I was working for JAXA over 34 years, very long years, and I joined the JAXA 1979, very many years ago. And at the time, my first work was the development of the active microwave sensor. This is a microwave scatterometer. This is just measurement of the radar scatter from the ocean surface. There's no information about the topography and the deformation as well. But 10 years after my career in JAXA, my job was my boss asked me to work for the interferometry and SAR development. And in 1995, at the time, I was very much interested by the detection of the deformation, and I was very much impressed by the very clear and very nice fringes given by the interferometry. Then I was working for or running for the interferometry. From the history of the study, almost 200 years ago, 1803, that is the middle of the Roman timing in Europe, and one great researcher named Thomas Young made the experiment. That is later the figure comes. The light has characteristics of the waves, and one signal emitted from one signal source split it into two slit that comes to the very low frequencies on the screen. These are prepared and this proved as light has characteristics of the wave. And the radar image was developed right after the World War II. And almost 150 years ago, after this experiment, one researcher proposed two signals emitted from the two radar can be interfered, and a similar signal can be detected. This is 1976. So interferometry was proposed by Dr. Graham in 1976. And 2 years after, very famous NASA satellite carrying the, I think, 3 active microwave instrument like a synthetic aperture radar, active scatterometer, microwave altimeter, plus microwave radiometer. Those 4 sensors was carried by this CSAT satellite. And NASA CSAT first proved this proposal given from the Dr. Graham. Later I can show. But this was, I think, the very important experiment developed by this very nice satellite, CSAT. After that, and 1 year after, I joined JAXA, and at the time I didn't know about the CSAT. But 10 years after that, I recognized CSAT did a very great job for the development of the radar technique on the interferometry, as well as the measurement of the surface change or the surface, the land surface. And after that, I think the many countries started to launch the synthetic aperture radar, as well as Japanese country. I was belonging to the Japanese Space Agency, and JAXA decided to launch the JRSN 1990 first originally, but 1 year shifted, 1992 started the operation. And we recognize, L1 synthetic aperture radar or C1 synthetic aperture radar can give us a very detailed surface of the Earth by using the interferometry. And accuracy has been improved after 2000, since the improved accuracy in time, position determination of the satellite or antenna, and orbital maintenance. All those components are improved as time goes. So I think currently, at the time of the 2020 or 2021, we have plenty of the satellite working from the L band to the C band to the X band combination or combination of those multi-frequency interferometry gives us very detailed surface change and surface conditions. And my talk just introduced the basics of the SAR interferometry. This one is a very famous figure developed by or detected by this. Sorry, I prepared this. There is a laser point. Yes, laser point. This is a CSAT. launched June 28th, 1978, many years ago. And this is second stage of the Sol Delta's launch, I think. And this is a scatterometer. My first job in JAXA was this one. So I like this scatterometer antenna, 3-meter antenna and Ku band frequency. But this is not the topic of today. And this one is synthetic aperture radar, L-band antenna. I think the length is 12 meter in advance direction and 2 meter in cross direction, emitting the signal to the land surface. And then this is a solar array. And this was operated over the equator, over the orbit, from June 28th to, I think, October, beginning of the October same year, almost 3 months. And here, when the satellite passes over this valley, one engineer produced this fringe pattern. This gives a topography of the Death Valley. This is fringe of the area express the height of the Earth's surface. So the combination of the two signals gives a height or topography of the land surface. Very impressive first light of the interferometry made by the CSAT. And after that, many countries, there is some message chat. When you ask question in slide, please write your name and institution and questions. And any question is okay, and you don't need to worry about interrupting my talk. And you can write down any question here. I'm happy to write answer. And here, let me see. How do I say chat? Okay, and there are the 4 satellite for 3 space-borne satellite. Here, and here, and right-hand side is right bottom is airborne synthetic aperture radar. All those 4 pictures are the synthetic aperture radar made by Japanese Space Agency. This one is very old-fashioned, 1992 to 1998, 6 years on orbit. This is no longer in a space. This was dropped onto near Antarctica, the end of the 1990s. And this is very origin of the Japanese SAR technologies. This is antenna 12.2 meter, emitting the signal right-hand side of the moving direction. And this one is a second generation of the Japanese satellite. This is so-called ALOS, Advanced Land Observation Satellite. And here is antenna looking the right-hand side of the moving direction. And this one, the biggest difference between here and here is improvement of the satellite position is perfect. In this time, satellite position accuracy is in the order of the 100 meter or less than that. But anytime we need the calibration of the positioning. But this satellite, ALOS, was launched 2006, and we are pretty available to use of the GPS or GNSS, very accurate positioning information. Then the interferometric processing was so much improved. We don't need to worry about the calibration of the positioning. We just need to worry about the water vapor time delay and ionospheric time acceleration forwarding. And this one is unfortunately dead, still on the orbit. And right now, Japanese agency is operating this ALOS-2. from the 2014 are still okay to alive. So I think this satellite is on the orbit over how many years? 5, 6, 7, 8, 9, 10, and this is the 7th year. And I believe this can survive some more years. And very good news for us is next year, after mission, Alos 4 will go to the space and in a same orbit, so that we can utilize two combination of the Alos 2 and Alos 4 for monitoring of the Earth. And this one is airborne synthetic capture radar being used for the very detailed observation of the land surface. We always looking for the airborne synthetic capture radar. Okay, and this one is Hanshin Awaji earthquake. This happened 1995, January 17th, 5:46 a.m., very early in the morning. This western part of the Japan was shocked by this very large-scale Hanshin Awaji earthquake. And at the time, JRS-1 was operating in the space, but in Japan, no such interferometric technology was available. Then I was asked by my boss to generate the psi interferometry deformation pattern caused by this Hanshin Awaji. This page shows two generations of the psi interferometry observed for this area. This area is epicenter of the earthquake occurred 1995, January 17th. And very early version of the interferometry, Sigmas produced this very wavy, strange pattern caused by the earthquake in this area. And on the ground, there is a 70 centimeter uplift across the fault here. And 5 years after, I improved this interferometry like here, connecting the northern part of the image and southern part of the image, southern part of the prefectures, and even there is isolated island here and another here, and normally discontinuity of the phase occurs, but successfully we connected this color pattern and this color pattern by changing the phase, connecting the phase in here. And one fringe shows half of the wavelengths because of this is repeat path interferometry. The change of the line of sight distance correspond to the half of the wavelengths. We use the L-band frequency is 24 centimeter. So from here to here, 12 centimeter. From the epicenter, fall to the edge of the eastern part of the island correspond to 70 centimeter. So we are shocked by from this image that the density of the fringe correspond to the surface collapseness and disaster. Then I'm going to the next page. What is a synthetic capture radar? I think the very early early time of this tutorial series, some more expert mentioned the synthetic capture radar. I just summarize the interferometry. Synthetic capture radar. Synthetic capture radar is the technique to generate the very accurate imaging, very accurate resolution imaging by adding the isolated images. By using the technology, high resolution imaging, from the very coarse imaging to the finer imaging, like here. This is image of the Hawaii island. But this is not the Japanese island. Japanese island. This is Hawaii island. The resolution is this size, 20 kilometers, but correlating the series of the pulses by using the weighting function, we can obtain the very fine resolution of the, depending on the bandwidth, in this case, meter order. And this is a pulsar image. So the resolution is 5 meter, very good resolution. And to do the interferometry, we start from the single look complex image. This is the amplitude image, but the psi image is normally generated as a complex image, amplitude and phase. What is a phase? That comes later. And complex data can be expressed by here. A times exponential 2 pi 2r by lambda times j. And this r is the distance from the radar to the ground target. And lambda is the wavelength that we are using in the measurement. In our case, Japanese Space Agency always operate the L-band. So this case, 24 centimeter. And this one is expanded to the cosine component and sine component, something like that. And this image cannot be visible. But when we have the absolute number, here amplitude, in this case, we can visualize the image, like here. But normally, complex image cannot be visible. And at the beginning, I mentioned that 1803, Thomas Young made the experiment. This is general of the experiment. He prepared the source, light here, and the light was emitted from, propagated through this very small slit, then expanding here. And he prepared the second slit here, slit B and C. And the light originated from this point is propagated through this slit and slit C. And this signal is generates the wavy pattern, something like that. This frequency depends on the distance between here, and also the distance from screen 2 and final screen. This is a Young experiment, 1803. And the similarity from this experiment, we can do the two signal source by the SAR in C and by the SAR in B. Normally, SAR costs so much. In a time of the ALOS, I have the number, but this is quite expensive values. And the ALOS 2 is almost half of the ALOS, but still very expensive numbers, very expensive satellite. And if we prepare, put one satellite here at point B and the same satellite at point C here. In this case, the distance between here and here and here are different. So in this case, we can generate the similar wavy pattern like here. So the origin or the origin of the psi interferometry is totally same as the Young experiment. So psi interferometry can be summarized here. This is first observation is here. Red satellite is moving. The height something like 600 kilometers over the Earth's surface and moving almost parallel to the Earth's surface with a speed of the 7.5 kilometers, emitting the signal in the right-hand side of the moving direction. Here, and the measurement was done by the distance, round-trip distance divided by the wavelength here. First time, this red orbit measure the center of this position here. The distance is R1. And several days after, the satellite come back to the same orbit. In this case, I use blue line here, emitting the same signal to here. But at this time, this position was uplifted because of the volcanic activity or earthquake or something. And this position was moved to this here. Second observation, the distance from here to here is slightly shorter than the first observation. If we zoom up this mechanism, here, the signal was emitted at the same phase from this position and propagating through the lens space.
Atmosphere. Yeah, space.
And here, and returned from here. And second observation is in here, but at the time, this point was uplifted in a way that the distance from here to here is slightly shorter than the first observation. So the second observation is here. So differentiation of this red experiment and the second blue experiment gives the phase difference of here to here, and we can colorize this measurement phase difference by like here. So this is a very basics of the interferometry. And we have the radar measurement has amplitude information like A and phase information here. If we show the amplitude information, this is 2007, April 2nd, we had a very big earthquake at the North earthquake, western part, 50 kilometers west of the North Peninsula. We had a very big earthquake, and these two images is comparison of the amplitude. In amplitude, we cannot see any change at all, maybe at all. Very difficult to detect where the amplitude was changed. But roughly speaking, both are the same. But if we do the phase difference between here to here, we can colorize something like that. This is arctangent of the imaginary part of the correlation of the two information divided by the real part of the correlation here gives here. So epicenter was here, and this point was uplifted towards the satellite direction. This was a quick look of the surface deformation of the North Peninsula using the interferometry. And the process flow is very simple. We have the two images, reference image and secondary. In previous, I just used master and slave, but recently we decided not to use master and slave. And sorry for this using. I forgot to replace those two words. And reference and secondary, those two images. Satellite moves almost the same orbit, but perfect same orbit was very difficult, almost impossible. And precise correlation of the two images is necessary. Then after that, output is given. So preparation of the first image, second image, correlation, and detection. This is a simple procedure of detection of the deformation. And when we look at the more detail of the position, this is one image, difference image in slant range image, secondary image. Those are co-registered, and orbit is maintained so that both two satellites can fly as close as possible, but reality is not possible. in average, 500 meter is average difference of the two orbits. But even so, we see the one image like here, and this image is composed of the many pixels. Here, white area corresponds to the 1 pixel. In the resolution, this is 5 meter and 5 meter in that order. And we zoom up this area to here. And this one is 5 meter expressing the 1 pixel. And here we this is a center of the pixel. And there is the variety of cases. One scatterer is existing here. Position is delta r from the center of the pixel and delta x from the center of the pixel in the direction of the azimuth. So delta x, delta r, using those two parameters, we can express the position of the scatterers. And this is a case, 1 pixel is involved in one scatterer is involved in a 1 pixel. But reality is not something like that. If we look at the real image, this is a drone image observing the land surface, forest area. The resolution is 10 centimeter, and I flew the drone and take a picture of some mountainous area, hilly mountainous area. And this is trees, and this is the land surface, and this is some dead trees and something like that. Zoom up of the area. This is 3 meter. Many scatterers are visible. This type, soils, sticks, and stones and leaves. Those are the component of the 1 pixel. So previously, I see the 1 pixel is composed of the 1 scatterer, but this is not like the real signal. Reality was something like that. 1 resolution pixel or 1 pixel is composed of the many scatterers. This point, this, so many. And you can imagine the 3 meter and 3 meter resolution pixel. And if we deploys many scatterers, I think the 10,000 or 5,000 scatterers are included. So the expression of the SLC for the 1 pixel is the summation of the AI exponential 4 pi RMI divided by lambda and j. This is linear summation of this component. And this 1 component is expression of the contribution from the 1 scatterer. But here 1 pixel is composed of the many scatterers. Summation is always necessary. The correlation is a key component of the interferometry. This is calculation of the correlation. This is reference signal and secondary signal. And C is composed of so many 10,000 scatterers. This one is included. And we expect we have the expectation processing of those 2 components. This is the way of the calculation can be modeled by that. This is 1 pixel, and this 1 pixel consists of the first scatterer, second, third, fifth, 10,000. And in a vertical axis, almost 10,000. If we do the correlation, only the component of this component, orthogonal component, has non-zero component, and otherwise has zero component because of the averaging processing. And this one shows this phase component, 2 pi, phi I, and phi j. Phi j is distance from the center of the pixel to the position of the scatterer. And this linear summation can be simplified, something like that. Correlation processing of the signal 1 and signal 2 can be done by the A plus JB times C minus JD. This can be simply expanded to the AC plus BD plus JBC minus AD. And this one is something like that. And this is finally, this one is a measurement. And this one is theoretically obtained. Be perpendicular Z by R1 sine theta delta Z plus B parallel. This one here. And measurement is equalized by the model, something like that. This is a perpendicular baseline and slant range, incidence angle, and topography of the height, and the deformation of the land surface in the line of sight, and parallel baseline. Basic equation, and parameter is here. And this equation can be is very simple, but this can be obtained by the Taylor expansion of the distance between S2's point P and M2's point P dash. You can expand equation. I did the calculation taking so many days. Well, finally we can generate a very simple equation like here. I will skip here. And again, this is master image, reference image, secondary image, and this is a real fringe of the data. Theoretical model is back up, and this one is differentiated. Then we finally obtain the final result, like here. Sorry. Yes, we out to the okay. And this is another very simple but very useful equation of the phase measurement is here, and deformation and digital elevation model, and standard deviation of the phase, something like that. This is a summary of the equation. I will skip because of the time. And this one is one close-up of the image. This is a zoom up of the North Peninsula. As I mentioned, from this color to this color correspond to the half of the wavelengths. We use the element 12 centimeter, 24 centimeter is the wavelength, and this is half of the wavelengths. Yes. And the frequency shift. This is another very important principle. Why as interferometry works, and when what is the condition to obtain the very good coherence or very good interferometry. And frequency shift is a theory that SAR1 is emitted the signal, and on the surface we have the wave number, and another satellite 2 gives emits a signal to the same position with a different incidence angle and giving the different wave number. But SAR has some limited bandwidth. We can shift the wavelengths so that the same wave number can be prepared. First image, satellite has a wave number spectrum on the ground here, and second one is here. If the satellite position is the same, this blue bandwidth and red bandwidth is the same, but normally those two are different. Then the common band area is limited. We have the point that the coherence becomes 0. This is so-called the critical baseline. This critical baseline depends on the bandwidth of the radar signal. In ALOS2, this has a bandwidth of 84 megahertz. In this case, the maximum critical baseline goes to the 10 kilometer. Wow, very good numbers. But I recommend to use 500 meter baseline dataset for the calculation of the interferometry. Unwrapping, this is a very important technique for interpret the signal. Unwrapping. And this is a flowchart of the signal processing. Two images can be generated, and phase measurement, correction by orbit, correction of the terrain data for the orbit correlation, and also rectification. Those are prepared, and deformation can be obtained. And this is basics of the interferometry. I think I take so long time, and I should speed up my presentation. I have 20 slides remained. And application.
That's okay, Sensei. Take your time.
Oh, yeah. Oh, yeah.
Yeah, we just need more explanation on that, but we can manage the time. Hopefully, you can spend another 10 minutes for your presentation for that 20 slides.
Oh, yes, 20 slides. Yes. Almost
yeah,
application.
That's okay. We can move it a little bit, 10 minutes for your question and answer session.
Okay,
thank you. Carry on, sir.
Yeah. Okay, thank you very much. I will introduce the two examples in my presentation. This one is 3D decomposition of the surface deformation. Almost 5 years ago, there was a very big earthquake near Kumamoto area. This is Mount Fuji area in Kumamoto city, and this is because of this big earthquake, our Kumamoto castle was breaking down. And currently this is recovered, but right after the earthquake, the surface roof was broken like here. And one example is decomposition of the surface deformation. The sound interferometry measures two-dimensional deformation in the line of sight. This is a combination of this red orbit and blue orbit, observing this component. If we have the two more deformation, almost the same time slot, in this case, we could decompose three line of sight measurement to the east component, north component, and up component as we measure the deformation from the GPS or GNSS measurement. So this technique is prepared for the 3D component decomposition preparations. Luckily, this satellite observed this deformation area right after the earthquake and right before the earthquake. First combination is observing this orbit, looking the right-hand side of the target area, and using this orbit component, looking the left-hand side of the flight. And orbit 3 observes the left-hand side in a descending path. So this gives this combination. The coordinate system is here. Deformation is expressed by the red arrow, like here, and by using the radar measurement, the deformation or deformation projected onto this line of sight is measured by the radar interferometry, one measurement. And we have the two more measurement. Then this can be we can produce these linear equations. Theta 1 is the incidence angle, phi 1 is azimuth angle, and phi 2 is azimuth angle at the second measurement. Phi 3 is azimuth angle in a third data set. Very simple. And as I mentioned, this is a relationship between the measurement and the theory. And this UW is unwrapped phase of here. Unwrapping is one very difficult technique, but recently there is a variety of software is prepared, like Snap, or actually I am not using. I'm using my own unwrapping software. This square type of unwrapping gives very continuous deformation mapping. And this 3D component of the deformation can be solved by here. This delta R0 is offset by doing the calibration. In our case, in Japan, we have so many calibration points in a center of the ASO area. In total, 7 different calibration points, and we just used this one. ASO ID number is 960730, and this, by using this information, we can offset like here. The unit is centimeter, east-west, south-north, and up and down. And this is data line of sight deformation, and this is also caldera, and this area was deformed, second one, and here. And this is a deformation at the center of the ASO area. Uchinomaki, very famous for the onsen, hot spring, and Kario. This gives almost 3 meter north to north deformations. And another area is Matoishi area, is another big deformation area. Here. So this is one type of the application of the interferometry. And second one is a time series interferometry. I think recently deformation very slight subsiding need to be monitored, and many local government is looking for the technique to measure the landslide movement. And there are several methods. SBUS, this is a very famous technique. PS-INS, also the famous technique. And there is prepared a lot of the literature, and you can learn from those SBUS and PS-INS. I'd like to show one technique, loop analysis and time series analysis. Zero baseline interferometry is very important. This is an equation of the interferometry. Measurement 1 and R1 and R3 is equal to slant range. This one times this one here. If we have the 3 times series area, slant range information can be given here. Time 1, time 3, time 1, time 2, time 2, and time 3. Those are always like here. So in this case, the phi 3, phi 1, 3 equal to phi 1, 2 plus phi 2, 3. If we have the zero baseline measurement, in this case, B perpendicular, B parallel, and B perp, those are the zero. Only there's the Z is non-zero because the surface is moving. So in this case, DZ13 and DZ12 plus DZ23. This is a fringe information. Under the zero baseline condition, deformation can be expressed by this one. Let's check out how this works. This is your country. Semarang area is a very famous land subsiding in the eastern part of the city, like here. And I apply 3 times series data set obtained by the ALOS I cannot see the 2008, 425, and 610, and 610 to 726. And this combination is 425 and 726. We do the differentiation of this one plus this one minus this one goes to here. This color is 0. So this zero baseline interferometry gives a loop measurement over here. Measurement, we can, if measures phase variation histogram, the center is 0.0607. So the phase is preserved. How about unwrapped phase? This area is slightly not 0, but here is 0. Peak area is 0.0510. So unwrapped phase and wrapped phase both gives preserves phase by the loop processing. Then we can apply this time series analysis, time 1, 2, 3, 4. Oh, 1, 2, 3, 4. And the differentiation of here to here, this is ideal. But during that, some surface deformation occurs. That gives a decrease of the coherence. But by using this technique, we can measure the deformation from this time to this time without reducing the coherence. This one is deformation from the April 25th to September 10th. This, and unwrapping of the here, unwrapping and unwrapping summation, and reduction of the 2D inclination by here. Then we have, this is the amplitude image, and this is a Google Earth image. This is deformation of the area. Assuming the deformation is just down to the Earth center, because of the we have only one ascending passes. So in this case, here the deformation is -2 or -5 centimeters subsiding in the right-hand side of the city, and here is almost 0 deformation. And this is error. This is error because of coherence is very, very bad. Forget about that. So just focus on this area. So using the zero baseline interferometry technique, we can measure the subsidence in a time resolution of 45 days, 46 days. Okay, so this one is actually zero baseline interferometry, and I did not apply the ionosphere and the tropospheric delay. We need to develop the diffractive index collection. Ionosphere, this is very important collection, and troposphere, very important collection. But in my presentation, I just introduced the scene that we observed from the processing of the pulsar L-band interferometry. This is ionospheric variation observed over the northern area of the Earth, over the Russian country. Sometimes we see the variation of the ionosphere. And here, this is tropospheric change of the characteristics. And normally the mountain whose height is over 1,000 meters or 1,500 meters typically sees the change of the tropospheric delay, and we need to collect those two informations. So, sorry for
yes. The final slides.
Final slide.
Yes,
This
okay.
is a summary of the sign interferometry. Sign interferometry can detect the change of the distance between the two equations in the red line of sight only when the pixel structure are almost preserved. And error sources for the insert are orbital deformations, determinations, and ionospheric error and atmospheric delays. Once they are calibrated, the accuracy can be 1 to 2 centimeters as relevant synthetic aperture radar. 3 azimuthal observations can provide 3 decomposition in east-north up component, 3 component. Time series data can provide the temporal change of the surface. Time series zero baseline interferometry can provide the temporal change of the surface. And this is a real final slide.
Oh, you got a book.
This is my book, and published almost 2 years and a half, 2 years ago. And imaging from spaceborne and airborne SARS, calibration and application. This consists of 15 chapters, and starting from the basics of the SAR interferometry and imaging, airborne synthetic aperture radar, and calibration, and forest observation, interferometry, everything.
Everything related to SAR applications, yeah?
Yes.
Okay.
So, please. Thank you for participation.
Yes.
Thank you for your participation.
Yeah, Domo Sensei, thank you very much for the presentation. Actually, as I said, learning SAR doesn't take short time. Yeah, it's I mean, you need to really focus. For me, 4 years to be in MRSL lab, it doesn't still give me a very good application and understanding on this SAR, because it's too much to cover. Yeah. And to understand that, you need to have a very good basic on mathematical and also formulations, etc., to be able to understand, because there are many kind of sites and others that you need to understand. And talking about interferometry itself, not only one, but like today you mentioned about these 3 visual line sight. That is a little bit new for me. Last time I only have 2 like that, right? So there are growing application, growing sciences as well for this application of SAR. So again, to understand that within like 1 hour lecture, it's not easy to grab whatever the explanation is. Besides our audiences, not all of them may be quite familiar with this synthetic aperture radar. But again, I believe here I've seen Yamaguchi Sensei's name as well among the audiences, but I don't know whether he's still here. There are other from Indonesian aeronautics agencies as well, from Geospatial Agency. I think those are applicators of these satellites data. So among the audiences, is there any questions? I look at the Slido. It seems like there has not been. Oh, okay. There is somebody is writing, Pak Oki Anggara. He is addressing you. Hi, Professor. I am very interested in your research related to deformation, especially the INSAR or DINSAR. Is the level of accuracy produced is good enough to know the deformation? And also the other question is, what band is good to use in determining deformation, and whether it can be validated by using GPS method? So these 2 questions from Pak Oki you can see in the slides, but I can copy for you in the chat room. Okay.
I think accuracy.
Yes, you can answer this question.
Accuracy is the issue.
Accuracy, yeah.
Accuracy is the issue, and I think my win is a calibration point as well, and. There are 2 types of the accuracy, 2 types of the error sources. One of that is offset. Second one of that is variation of because the phase is kind of the characteristics numbers. And first step is to determine the offset. And to determine the offset, we need a calibration point. For example, GNSS station gives real position of the scattering point. And this is once the point was phase is measured, I think the standard deviation of phase goes to less than 1 centimeter. Other than that, is the ionosphere. Ionosphere is a very tough target, depending on the variation of the ionosphere.
Yeah.
Ionosphere, if even the thick ionosphere, this is okay, but the variation of the ionosphere is very tough target.
That's why the atmospheric correction is also very determine the accuracy, Sensei.
Yes.
Right.
Yes.
Okay, the other one is about what band. I believe there is certain L band, X band, and C band. Which one is good? I write out in the chat in there. What band is good to in terms of determining deformation?
I think everything has different characteristics, and recently by now the longer wavelengths is very good for the interferometry. This was said that long wavelength is better for the interferometry, but recently Sentinel is coming back to the same position every 12 days, I think. So the very short revisit time interferometry is can even the shorter wavelengths. If the revisit time is small, in this case, they can give the very good accuracy of the interferometry. But from the basic users, I recommend to use the longer wavelength.
The longer band.
Because coherence can be easily obtained.
Right.
Interferometry can be easily produced.
Okay, because baseline is also determining the conditions.
Yes.
I remember last time when I used Sigma SAR, the two images that I have to make for interferometry must not exceed the baseline is used for the two images. Yeah, like that.
But
okay.
Yes. The case, I think most of the data pair is less than 1 kilometer.
Yes,
so
yes.
You don't need to worry about the selection of the data to generate the interferometry for the L band.
Right. Yeah, Sensei, time is soro-soro. It's already 15 minutes. Right. But we really thank you for your sharing with us. Joseph Sensei would like to say something. Yeah, dozo, Sensei.
Okay, yeah. Shimada Sensei, thank you very much for your nice presentation and tutorial. Yes, I think it's all of the participants, yes, including me, is learn much is from you. Yeah. Thank you very much again.
Thank you very much.
Keep healthy. Yes, and safe. Yeah.
Thank you very
and
much.
If you can send us also the presentation material and the book. Is the book available on where? In Google or anywhere we can buy this? Because I'm personally interested to buy the book.
Okay. Thank you.
I might send you an address and send it directly to you then.
All right.
Okay. Yeah, thank you very much, Sensei. Thank you. Domo arigatou gozaimashita.
Thank you very much. Yeah, Shimada Sensei.
Hi, domo. Hi. And the next speaker with Steven Gao Sensei, Professor Steven Gao is with us. Yes.
He already come.
Yeah.
Yes.
Oh, he's already in the room.
Yes, that's right. Yes.
Hi, Stephen.
Yes.
Yes.
Hello.
Thank you very much. Yes.
My pleasure. Thank you.
Yes.
Yeah, this is live from UK, Professor Steven.
Yes, that's right. Yes. Can you hear me?
Yes, we can hear you clearly.
Excellent. Good.
Yeah.
Do you want me to share the screen or?
Yeah, not yet. I was just asking you whether you are alive from somewhere.
Okay.
Yes,
from
usually
UK,
I just read a brief CV of you before you give your lecture.
Okay. You can just briefly because we have been short of time. Yes.
Yeah, sure. Just in brief, our next speaker is Professor Steven Gao. You might be mistakenly if he's in China, but he is in UK. He received his PhD from Shanghai University, China, yes. But now he is a full professor and chair in RF and microwave engineering. And now he is the head of communication research group at the School of Engineering and Digital Arts of University of Kent in the United Kingdom. His research covers mostly about antennas, smart antennas, phase arrays, reconfigurable antennas, and many other more that I don't have to read all of them. He has a book and he co-authored 3 books. You can have a look at this about the space antenna. He is a fellow of IEEE, of course, a fellow of Royal Aeronautical Society UK, and also a fellow of IET UK. He was a distinguished lecturer of IEEE Antennas and Propagation Society and served as an associate editor for several international journals. There are many other more journals belong here that he lead and also authored. So there are a lot of publications on his behalf. So as I mentioned, this Professor Steven Gao is very well known in terms of antennas research. Finally, he is the representative for UK in the Republic and the Republic of Ireland in the European Association on Antennas and Propagation. So as you can see from his brief biography, we will have a lecture and also about this tutorial related to antennas. Yeah. So the antennas for the SAR. So what kind of antenna is specially designed for synthetic aperture radars? We will have a lecture about this with Professor Steven Gao. So, sir, I know that the time is limited, but we are moving it a little bit 10 to 15 minutes later because of the timing of some kind of discussion as well. So take your time. You can have a half an hour presentation and we can have a discussion afterwards.
Thank you, Chairman.
Yes.
Thank you.
Okay. You can share your screen if you want.
Okay, thank you.
All right.
Can you see the screen?
Yes, the screen is clear and your voice also clear.
Okay, thank you.
Yes.
Good afternoon.
Time is yours, sir.
Thank you. Thanks for Chairman for the introduction. Good afternoon, everyone. I know everybody's hungry now. It's kind of late afternoon in Indonesia. Probably everybody want to going for dinner, probably. Yeah. So I will try to keep it brief. My name is Steven Gao, originally from China. Yeah. From University of Kent now. The title is Antenna for Spaceborne SAR. First, I want to thanks to Professor Sumanto, Chiba University, who is the General Chairman of APSAR 2021, for a kind invitation for giving me the opportunity to give this presentation. Yes, many thanks, Josh. This presentation we'll talk about the project called Different. This is a project collaborated with many partners in Europe, including University of Kent, DOR in Germany, and the University of Calabria in Italy, HP, and Electronics in Poland, and ISS in Netherlands. And in the University of Kent, in my team, Dr. Mao, Dr. Qing, and Dr. Wang, they contributed to the project. And DOR, Anton, Tobias, Carolina, and Marvin, they all made very important contributions to this project. And Professor Luigi Borsia, Emilio, and Gian Domenico from University of Calabria in Italy, they all made very important contributions. Some slides from this talk from Anton, who's from DR, and this funding from European Commission, the project called Different. The tutorial today is kind of basic level because the time is quite short. So I will briefly introduce some basics of antennas, then talk about the SAR in different projects. So this is for mainly undergrad and postgrad students in electronic engineering, communication engineering, physics, or some other subjects. First, I will give an introduction to University of Kent, then briefly talk about the antennas in SAR. In the third part, I will talk about the SAR in the different project. This SAR is called, it's kind of a dual band, K and X band, and it's using DBF. DBF means digital beamforming. So this is the next generation SAR for the Europe's spaceborne remote sensing. I will talk about the mission concept and the system architecture and the antenna systems, of course. Yeah. Then briefly talk about the other subsystems, IF-board and MRSC, ADC. Then finally conclusion. Time is quite brief today because I got another meeting around 6 o'clock. So basically I got 40 minutes, or 30 minutes, I must run for the next meeting. Yeah. So if you got any questions, please feel free to drop me an email. I will try to answer in email then. University of Kent, we are in, the University of Kent is in a city called Canterbury. Canterbury is very close to London. We all know London, right? It's the capital of UK. This is London here. The Canterbury is the south of London. By train, it's 50 minutes. It's a very, very short distance. It's along the coast. So, yeah, so this is where we are. This is the antenna microwave research team. I have 8 colleagues, academic staff. Then every people got his own research group. So it's quite a large group. The microwave research group at Kent was formed by Professor Parker in 1968, which is almost, 43 years ago. Yeah. Oh, sorry, 53 years ago. Yeah. We claim we are the leader in smart antennas, phased array, space antennas, frequency structure service, and filtering antennas. These are our facilities. We have the antenna chamber, near field measurement systems, and the far field, the plane wave anechoic chamber. The measurement of antenna system is from 500 megahertz to 110 gigahertz, and also have the network lines and the spectrum lines up to 300 gigahertz, and we have mechanical workshop to manufacturing. Also have some other manufacturing facilities. For example, we have 3D printing facilities for additive manufacturing. The second part, I will briefly introduction to the SAR antennas. The previous speaker have given a brilliant talk about the SAR systems, so I wouldn't repeat it. Yeah, SAR, because I'm sure everybody knows better than I do. Yeah, I think I noticed the previous speaker also have a book on SAR remote sensing, which is brilliant. Yeah. SAR, as mentioned by the previous speaker, is a synthetic aperture radar. So it's basically using the movement of a platform to synthesize a larger size antenna to form high resolution. So what is antenna? Antenna is a device to receive or transmit radio signals. This is a photo of the dish antenna you can see in many buildings, well, on a roof of many buildings. This is a typical reflector antenna for receiving satellite TV signals. Actually, there are many, many different types of antennas. This is just one type of antenna. Radiation pattern is a key parameter for antennas. But if you talk about antennas, you must know what is the radiation pattern the antenna produces. This is a typical radiation pattern of antenna. You can see it has a main lobe. Main lobe is this is the radiation towards the direction we want. Basically, the most of energy is concentrated in this direction. We also have back lobe. In the back lobe, basically, the radiation is towards backwards. This is not the direction we want, but unfortunately, any radiation from antenna will have back lobe because it's impossible to concentrate all energy towards the direction you want. Of course, in the antenna design, we want to minimize the back lobe because the back lobe radiation is a waste of energy. Also, it causes interference. Also, there's a side lobe. You can see side lobe, which is also radiation towards the direction we don't want. So in antenna design, we want to focus energy in the main lobe. We want to reduce energy towards the back lobe and the side lobe. Also, there's 3 dB beam width, basically the half power range, angle range. Dipole antenna is a very popular antenna. This is called in this antenna. You can see the photo of the antenna here. Basically, sorry, somehow, yeah. Basically, it's a piece of metal, this antenna section at the top. Then you have a feeder section at the bottom. The antenna section is a metal wire, which has a length of half wavelength, lambda divided by 2. Lambda is a wavelength. So basically, the length of this antenna is dependent on the wavelength. So the smaller, the lower the frequency, as we know, the larger the wavelength, which means the antenna is larger. If the frequency is very higher, then we know the wavelength is small. In that case, the antenna size is smaller. So this is a dipole antenna. This shows the current distribution on a dipole antenna. You can see current flowing, and also you can see the electric field distribution on the dipole antenna. Dipole antenna is very simple. Well, let's say most basic dipole antenna, but it's very popular. This is a photo of the dipole antenna. You can see the left side is a dipole, then the feeding structure. The dipole, as we said, it has a length of lambda over 2, half of a length. There's another type of antenna. Oh, sorry, this is radiation pattern of dipole antenna. The radiation pattern of antenna is like an apple, yeah, or donut. It's the direction. This is called omnidirectional pattern. Another type of antenna, very popular, is called a monopole antenna. This is a monopole antenna. The monopole antenna has a length is lambda over 4. This is different from dipole antenna. Dipole antenna has a lambda over 2. But here, monopole antenna, the length is lambda over 4. There's a metal ground at the bottom. Then this is a feed. The feed can use using coaxial cable. Yeah, coaxial cable. Why the monopole antenna only need a length of lambda over 4? Why and dipole has lambda over 2? Why is the difference? Actually, the monopole antenna can be seen as equivalent to the dipole antenna. Now we compare them. On the left side of figure A is a dipole antenna. Dipole has a length lambda over 2. And on the right side, which is figure B, the monopole. Monopole is a metal wire, has a lambda over 4 length. There's a metal ground at the bottom. Because of the existence of the ground, metal ground, the monopole will produce image below the ground. The image and the monopole combined together is equivalent to the dipole antenna. So basically, the reason the length of dipole, a monopole is a lambda over 4, is because we have a ground plane which can produce image below the ground. So effectively, the monopole antenna, despite the length only lambda over 4, it's equivalent to a dipole antenna with a lambda over 2 because of the metal ground. This monopole antenna is very widely used. You can see monopole. This is a monopole antenna on the top of a roof. You can also see this monopole on some other applications. It's a very basic type of antenna. It's because the lambda over 4, so the length is smaller. And it's easy using metal ground. Here, the car roof serves as a metal ground. Another type of antenna, which is very popular, called a patch antenna. Sometimes we call microstrip antenna. What is a microstrip antenna? It is a metallic strip or patch mounted on the dielectric layer or substrate, which is supported by ground plane. So what we have is this is a patch. Basically, it's a metal pad, metallic patch at the top. And there's a ground plane at the bottom. Between them, we have a dielectric substrate. The substrate has a thickness, is H. H is the thickness of substrate, can be a few millimeters or even less. So very thin. The length of the patch is L. The L length of patch is very important. It determines the frequency of operation of the antenna. The width W also very important because the width of W determines the impedance matching or the bandwidth of the antenna. So this microstrip patch antenna. Of course, here the rectangular we use a rectangular patch the patch has the shape of rectangular. But because the fabrication of the antenna is just using printing technology, so basically you can print any shape. Doesn't have to be rectangular. You can print any shape. This is side view. You can see at top we have a metallic patch. Bottom is ground plane, and the thickness of dielectric substrate is H. It's very thin. It's called PCB, printed circuit board. So fabrication is very easy, just using PCB technology. So it's low cost, very lightweight, and easily conformal to different shapes. So this is a photo of a rectangular patch antenna. You can see patch, rectangular patch on top, and the ground plane at bottom, and this dielectric substrate feeding through magnetic line. So it's very easy for manufacturing and very small in size and lightweight. As mentioned, the patch antenna, one of the most important advantages is very easy for manufacturing. It's very flexible. You can print any shapes in real world manufacturing. So we can use a square shape, rectangular shape, dipole, circular, triangular, any. So it's very flexible. Different shape sometimes can produce different performance. So in the design, the many choice you have, very flexible. The patch antenna elements, one element can produce the antenna gain relatively low, but what it can do is it can combine many antenna elements from antenna array. For example, this the top is how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 16 elements. 16 elements antenna array. Combine them together. You can see this is a feed line. Combine the power from each antenna into one input port. So in that case, it can achieve very high gain because it combines the gain from 16 element array. Also, on the left side is another same thing, but also 16 element array. Also have 4 element array. Here is 1, 2, 3, 4. 4 element array combined together. Or 8 element. Okay, depending on design and the system requirement, you can choose different type of antenna elements and how many elements and what kind of arrays. Can it be linear array like this? Can it be 2-dimensional array, even 3-dimensional array, depending on the system requirement. The beauty of this antenna structure is very lightweight, or compact size. Easily you can put this on satellite or on aircraft. It's quite easy, and it can conform to the curved structure as well, because the substrate is very thin. Can be easily depending on thickness. If you choose a very thin band, 0.1 millimeter, for example, or capital, which is a very thin substrate, can conform to the curved shape, which is very useful in some cases. So this is a printed antenna array, and the fabrication is very easy, just the printing technology, so low cost. This is a SAR antenna for the CSAT SAR. CSAT was mentioned by the previous speaker as well. This is this SAR was launched in 1978 by NASA. You can see this patch. This is 2-dimensional patch array. Here the antenna array is big compared to, you can see the lady. It's very big. Why is it so big? Because this antenna operates at L band. What is L band? L band is around 1 gigahertz. Because the frequency is low. When frequency is low, then you have very long wavelengths. Then antenna size is bigger. If you go to much higher frequency, let's say go to millimeter wave, K band, for example, if you go to high frequency, then wavelength is smaller. In that case, antenna size is smaller. The length of the patch antenna, the length L is roughly λ/2. So this is antenna for CSAT SAR. Space-borne SAR systems has lots of challenges. For example, how can we achieve high resolution? Also, we need a wider swath at the same time. These two requirements are contradictory. How can we achieve both? Also, we want typically a space-borne SAR system with very bulky and very heavy, very power-hungry and complicated structure. How can we reduce the size, mass, power, and the complexity? Because if the structure is very complicated, typically it's very expensive, right? So because we don't want something expensive, we want to reduce the cost. of spaceborne SAR system. So if you reduce the cost, how can you achieve high resolution and wide swaths? It's not easy. We need a new solutions. That's why need a new generation of young engineers like scientists like you all audience here. Hope you can find the better solutions to tackle these challenges for spaceborne SAR. The third part, I will talk about the SAR project, different, which is a project we finished a few years ago. Basically, this is digital beamforming SAR system, which is a KX dual band. Different project has many partners in Europe, as mentioned before, DLR and CAN, etc. The purpose is we want to achieve digital beamforming SAR system with dual frequency band, which is KX dual band, dual polarization, and also we want a low cost, because we mentioned before, spaceborne SAR system is very expensive, which is not good, because at the moment there are lots of requirements for spaceborne SAR system on board small satellites. Small satellite is cheap, we know. If the SAR system is very expensive, doesn't make sense, right? So reduce cost is crucial. And we need a highly compact system, so which need to be highly integrated, compact size, to involve many partners in Europe. We have a website called different project in EU. Basically, because time is brief, quite limited, I just briefly mention digital beamforming. In the case of digital beamforming, we have many antenna elements. Each of these represents one antenna element. Here I have 6 antenna elements. Each of them connecting to the switch, which is for receiving or transmitting. RX means receiving. TX means transmitting. Switching to transmitting or receiving mode. Then have amplifier, then have filters. ADC means analog to digital converters. Then digital beamforming. Digital beamforming DBF SAR. Digital beamforming called DBF. DBF SAR. Advantage is it can have multiple channels, and you can use very clever algorithms, and beams can have adaptive shapes and improve performance, and advanced modes, and different modes. So very flexible. This slide compare analog and digital beamforming. On left side, you can see 1, 2, 3, 4, 5 antennas, each of them connecting to phase shifters and amplitude control. Then combine them, then AD converter, finally, then SAR processing. This is typical phase array, because it controls the phase of each element and achieve beam scanning. But the disadvantage of this one is you can only have one beam, right? Beam scanning, but one beam only. And right side, if you choose digital beamforming radar, you can see antennas. Here have 5 antenna elements, each of them connecting to mixtures, down converting to lower frequency. Then AD converter, analog to digital. Then this becomes digital signal. Then using digital beamforming, so you play with very clever algorithms. Then use the SAR processing. The advantage here is you can form many beams simultaneously. This is different from the analog beamforming on left side, which has one beam on it. On right side, digital beamforming can have multiple beams, and each beam can be adaptively shaped. Yeah, so much more. So you have using DBF, you have much more flexibility compared to the analog method on left side. So that's why we choose DBF. We believe this is a trend for future systems. Digital beamforming is a trend for future. Now, briefly, I introduce the mission concept. Basically, we want wide area illumination for SAR system. In that case, we use less antenna elements. In that case, you can have higher gain, low gain. Low gain means wide beam. So in the transmitting, we're using low gain antenna for wide area illumination, right? This is for transmitting. For receiving, we're using high gain antenna. In that case, by using high gain antenna, we achieve high resolution. But then we're scanning the beam in the receiving case, can achieve wider swaths and also high resolution. You can see transmitting with wide source thing is transmitting wide source beam. Then in receiving, have high gain beam, but scanning, so we can cover all the area we want. This is called digital beamforming on receive. In this way, we can achieve high resolution and a wider source simultaneously. So this is the idea, key idea here. So this, how do we realize them in reality? In reality, we use the antenna called a reflect antenna, feeding with a feed array, digital beamforming feeding array. This is a feed. You can see the feed has many elements, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 feeds, just as illustration here. If you use one feed, illuminated reflector, then you can have very high gain. In that case, to high resolution. But you can move the feed. In that case, you can achieve beam scanning. Move the feed to the left side. You can achieve the beam scanning towards the right side. So achieve beam scanning this way. But in the case of transmitting, we excite all the feed. In that case, because of the feed, you excite so many of the feeds, the feed will achieve narrow beam. It can only illuminate a small part of the reflector. In that case, the gain of the whole antenna system is small, has a wide beam. So this achieves a wide beam coverage, wide source. But for receiving, we use high gain. In that case, by scanning the high gain beam, we achieve high resolution. So this is a DBF with reflect antenna. What we need here is we need a digital beamforming feed array for feeding the reflector. This is a spaceborne platform. You can see we have the Ka band transmit antenna at the bottom. Also have K and X band dual band antenna for receiving. This antenna will be putting on the boom, because the reflector ray or reflector will put on the beam. Then if the reflector will be fed by called an integral feed system, which is digital beamforming. So this is a feed for reflector. The feed, basically, we use a method called a chip on board. Chip is a circuit, right? On board is a printed circuit board. You can see at the top, you can see how this structure has multiple layers of antenna elements and the module board and the MMIC chips, digital beamform chips at the bottom. Then all this structure will be integrated. So it achieves a high level of integration and compactness of digital analog, IF, and low frequency putting together in the same board. So this is system architecture. You can see on the left side, you have radiating board, which means antenna system. And then you have I front end, which means all the circuits, MMIC circuits. Then you have digital backend, digital backend, which means digital beamforming structures. So all these will be putting together, integrated into multiple layer structures. Antenna system has many challenges, as we mentioned. It has firstly needs to operate in multiple frequency bands. Also need a broadband matching at each frequency band. Also need dual polarization with high resolution, high isolation. Need a shared aperture, because you can use one antenna for one frequency band, which is not good. Ideally, use one aperture for all frequency bands you need. So called shared aperture, basically single aperture for covering multiple frequency bands. And also need the beam scanning, multiple beams, beam shaping, and high integration, common size. Also need to consider space environment and small size, lightweight, local. So many challenges. So it's a very difficult design antenna system, because you actually not just design antenna. You need to consider circuits, because antenna, circuits, the system is not separated. They are integrated. They're linked together. So you design antenna, you must consider the system, the circuits behind it. How do they fit together? So this antenna system can see the reflector and the feed. The feed is a planar array, basically the digital beamforming planar array. The reflector is a deployable antenna, a deployable offset reflector antenna system. This is a feeder system, the antenna array. You can see it's a patch antenna, but it's using different type of printed antennas. For example, for the X band, we're using cross dipole antenna. For the K band, we're using square patch. As you can see, the size of the square patch and the cross dipole is different because they operate on different frequency band. And the X band is frequency is lower, so the wavelength is bigger, which means the size of the cross dipole is much bigger than the square patch at the K band. Yeah, right. So, so this combines the cross dipole, which is why we need a cross dipole, because we need a dual polarization, right? Similarly, for a square patch, we need a dual feeder for dual polarization, then combine them together into the single aperture using multi-layer structures. So this shows the structure using multiple layers. The cross dipole is put in the top layer, then the patch at the lower layer, then slot coupling at the bottom. You can see the figure on the right. You can see cross dipole at top layer, then patch at the lower layer. Patch, of course, here patch using multiple layer as well, because you need a wider bandwidth, wider band performance. So you use multiple patches instead of single patch. This shows the integration of antennas and circuits. You can see using many wires because connecting patch and antenna and the circuits and the digital forming chips across different layers. I think time running out. I'll just rough out quickly. So basically, you can see this is side view of the structure. You can see many layers connecting using wires. The fabrication, it's not easy actually. Yeah, this is a photo of the front view and the back view of the system. Yeah, this is a measurement result. You can see X band results. Good matching high isolation between the two ports, and also K band, which is 30 to 38 gigahertz, much higher frequency bands. You can achieve good isolation as well. So dual polarization at both X band and K band. And this is rotation pattern. It achieve low cross polarization and high gain. This is the antenna system with reflector antennas and the feeder combined together. The system can achieve the gain. X band is 39 dB and K band about 55 dBi. Right. Apart from antennas, there are many other systems. For example, F-board, MMSC, ADCs. When you design antennas, you must consider all of them together, not just because antenna is not separate. So you need to understand the DBF behind the antenna system. So this is GBF building blocks. Because time is yes, we're running out of time. I'm not going to details. This is integration between the different parts. This is again shows the side view of the structure. You can see we have in total have 16 layers. 16 layers. Yeah, all these layers, fabricated together. Yeah, this is the MMSC and all kinds of chips at the bottom, then antennas on the other side, then connecting together. This is MMSC integration. MMSC is at both K and X band, dual band as well. Then integrating with antennas, MMSC, and ADC all together. This is a K band chip, a receiver chip photo, and this digital beamforming network. Right, this is a FPGA control because in the control system. Yeah. So I'll just wrap up quickly. Right, today we briefly introduce the sound antennas, then briefly introduce the dual band KX, dual band highly integrated dual polarized digital beamforming SAR system in a project different. Recent years, there's a SAR system called a circular CP SAR proposed. This is invented by Professor Shimada. CP SAR is a circular polarized SAR system. If you need to understand the CP SAR, the antennas in CP SAR, we actually write a book called Circular Polarized Antennas. This can help you understand the antennas in CP SAR. If you want to understand CP SAR, please read the papers and books from Professor Shimada. Yeah. Also, we have a book called the Space Antenna Handbook, which is talk about the spaceborne SAR antennas, etc. This is another book we published recently called Low-Cost Smart Antennas. Thank you. I hope to see you everyone here at the ABSAR 2021 in November. Again, many thanks to Professor Simento for the kind invitation. Thank you.
Yes, you're welcome, sir. You're welcome, Professor Steven Gao. Unfortunately, you have to go, yeah, during this time.
Yeah,
but, yeah. Sure. We cannot hold you, of course, because if you have something to attend. But any questions from the floor, any other question from the audiences can be written to email, or will you have any minutes at all, or you really have to go by now?
I really have to go. Yeah, sorry. Yeah.
Sure. We understand your busyness. As I know in UK, you might be still have to do something else, but we do appreciate very much on your lecture. I know lecture about antenna is not also that easy to grab and to cover, but at least your insight to us already give us some understandings of this antenna. One just little question, Professor Steven Gao, for me personally. Antenna is made in different varieties of material. Can you explore the elaboration of this kind of material used to make this antenna? Because I'm not into antenna myself, but how else the material be different in terms of producing? Will that be any certain material only can be used? Can you comment on this?
This is a very good question. Actually, material is a very important part for antennas.
Yeah.
Actually, nowadays, one of the big innovation of antenna system is you play with new materials. For example, if you in old days we use the traditional material for a PCB board, but nowadays people look at the new materials like the tunable material. The material basically, in old days we have a permittivity antenna of material fixed. Then you have antenna with a fixed performance. But nowadays we need to have material which is tunable. Basically, the material, if you change the DC voltage of material, the material can have different electrical performance. In that case, you can change the antenna performance as well. So one of the hot topic in antenna system design is using tunable or smart materials for achieving very good performance. But there are many different type of smart antennas. People using graphene or using liquid crystal, and some people using JST material. So this is a very hot topic, actually, very hot topic. Yeah.
So there is a special research on the certain material that used for certain antennas, yeah?
That's right. So. Yeah, in particular, called smart material for antennas. Smart material.
Okay. Yeah. Okay, Sensei. I mean, thank you very much for this opportunity. Prof. Josh is still here. You want to say something
I have
Professor Steven Gao?
Question. Yes, to Steven.
Hi, Josh.
In your antenna, you use, right now it's not yet for the space environment.
No.
Oh, not yet. Oh, okay. Yeah. Actually, in my laboratory, we develop for high temperature material. Yes, for the antenna. Yes. Yeah, maybe we can discuss later. Yes.
Yeah. That's very useful.
Now we develop the antenna for the temperature is more than 500 degrees Celsius. Yeah. Because amazing. We want to to observe closer to the sun. Yes, it is more high temperature. Yes, of course. Now we consider it from the spaceborne one. Yeah.
That's another issue.
Yeah, very important, because for space environment, you need to make the material make sure it can survive high temperature and low temperature. So this is very important.
And also we consider also the radiation. Yes, the effect of the radiation. Yes.
Okay. Very good. Yeah. Thanks, Josh.
But thank you very much. Yes, for nice. The progress of the difference. Yeah.
Thank you.
Maybe I joined 2 years or 3 years later ago. Yeah.
Actually, thank you for Professor Josh Simento. It's a review of this project. Actually, thanks, Josh, for the support. You're supporting our project. Thank you.
Yeah, everyone, ladies and gentlemen, please. We have to say goodbye to Professor Gao because he has to do something. So, but in the future contact, future references, we can give you his email for further contact to learn.
Yeah,
Yes.
please drop me email if any questions. My email is s.glo@kent.ac.uk. Yeah. Thanks, everyone.
Yes, it's
Yeah.
available there. Thank you, sir. Thank you very much. Bye-bye.
Yes.
Thank
Thank
you.
you very much. Yes, Steven.
All right. Yeah.
Bye-bye. Thanks, Josh.
Keep
Yes.
healthy. Yes.
Yeah, you do. Thanks. Bye.
Bye. Okay, ladies and gentlemen, that's is the end of the third speaker session. Unfortunately, we are also limited by time. As a moderator, I think I concluded my assignment as moderator for today. I would like really to thank Professor Josephat for this opportunity, the general chair of this APSAR conference. As I mentioned in the beginning, there would be probably a continuation of this tutorial series, as I mentioned in the beginning. Would you like to say something about this before we close, Sensei?
Oh, yes. Thank you very much, all. Yes, to join us is about 3 hours. Yes, I think it's you could learn much about the the polarimetric SAR from Professor Avik, and also the INSAR. Also some the INSAR itself is very important, and I think it's a good application. Yes, with the high accuracy, and right now is like Steven is also developed the more efficient and low cost of the synthetic aperture radar for the spaceborne one. Yeah, and of course we also developed some sensor. Yes, the new sensor for the future sensor. Yeah. Okay. I encourage you to join the Aperture 2021, and the deadline is June 30. Yes, please consider even you're doing in the field of the remote sensing or some like noise, the trend is about the IoT, and if you can combine with the synthetic aperture radar on the remote sensing, is we welcome all of you. Yes, and I hope we can prepare as best as possible, even the condition of the COVID-19, and yes, if possible, is we want to continue, this tutorial program. Yes, to for the capacity building of young scientists, especially in the Southeast Asia, to use the synthetic aperture radar technology as much as possible. Because right now it's like the Sentinel-1A, 1B, ELOS, and then also the TerraSAR X, and many, including the RadarSat. Yes, you can use, and especially in the Sentinel-1A, 1B is free of charge, and you can also try using the SNAP. Yes, from the ESA. Yes, it is also free of charge. Even your students, you can use. Yes, and the time interval is 12 days. Yes, it is a good opportunity for us to use and to improve our knowledge in synthetic aperture radar. Yes, I encourage of you, and okay, and then okay, the tutorial, and then the Aperture itself. Yes,
yes.
I hope, yes, we welcome of you, and then
yes.
As the IEEE GRSS, yes, I'm one of the leader of the IFT, yes, instrumentation and future technology. Yeah, I hope next month, yes, we will open the competition of the UAV, yes, for the future technology, including the UAV itself, and also some sensor, yes, and also some what is tool surrounded the UAV. You can propose, and you can, it is because world level of the competition. Yeah, and I hope some of you from the Southeast Asia also join this competition.
Yeah. I see some names.
Yeah, and I will prepare some trophy. Yes, trophy for you. Yeah, and
okay.
For the trophy is we will deliver in the opening ceremony of the Aperture 2021. Yeah.
Okay.
Yeah.
Thank you very much, Professor Josh.
Also,
one more.
I encourage you to do the research, the good research, yes, best research, and then please submit to IEEE JRSL. Yes, I'm to be. I'm right now is the associate editor. Yes, and I hope we can, increase the number of the paper in the JRSL. Yeah.
Thank
Okay?
you. Thank you, Professor Jos. But I would like also to please the general, the vice co-chair, Mr. Wahyudi Hasbi is here.
Oh yeah. Okay.
I saw his name from the beginning, from the first session.
Maybe
Pak Wahyudi,
Wahyudi has to.
if you are here, please say something related to our.
Yeah.
Silakan Pak Wahyudi.
Yeah.
Silakan Pak.
First of all, thank you so much for Dr. Ilham for your great moderation for today's session, and of course also from the very great support from our sensei Professor Josaphat for all the tutorial series so far. And then we encourage, as Professor Josaphat mentioned, that we encourage all the young scientists, young engineers in Indonesia to participate in our EPISAR 2021. Actually, this tutorial is a pre-conference tutorial for all of us, so that we expect a lot of papers coming from Indonesia, of course, and also from Southeast Asia, of course. And then my last comment is I do believe that we will need more and more tutorial series because this is very interesting topic and very new topics for Indonesia, and we do hope that Indonesia will use all the SAR satellite image in many years from now. So thank you so much, Pak Ilham, and also Josaphat Sensei for great effort for all this this tutorial. Thank you so much, sir.
Yeah. Thank you, Pak Wahyudi, the Vice General.
Maybe Pak Agustan has some message. Yes.
Is Pak Agustan still here?
Yeah, the chief of the Indonesian Remote Sensing Society.
Yes. Yeah. Is he here? Hello, Pak Agustan. He said that he won't be here until the end of the session, Sensei.
How about Professor Ketut? Professor Ketut here?
Professor Ketut, I didn't see his name from the first session.
Oh, yeah.
Yeah. But ada Gede.
I saw Dr. Yuyu here. Dr. Yuyu is our leaders also from Jawa Barat Himpunan Research. Yes, please.
Oh, good. Yes.
Yes.
Pak Yuyu,
silakan.
some
Please.
message.
Yeah, please, Pak Yuyu.
Okay, thank you for your attention. I will submit a paper in FESR. Yes, I will. Yes, I hope the Indonesia can make the Sharmet in Indonesia. Yes.
Yeah.
Maybe Lapan can be made. Okay, thank you.
Thank you very much, Pak Yuyu. Yes, I hope we can do some project in Indonesia. Yeah.
Okay. Yeah. Of course.
Okay, Sensei.
Yeah.
Yes. All right. Anybody else would like to say something before we finally close the tutorial today? If not, I would like to invite the MC. I would give back to the MC just to have our closing of the tutorial. Nisa, are you there?
Yes, I'm here.
Yes. Okay. I return back to you as you are the one who started as an MC. So now let's just close our tutorial for today. Time is yours.
Yeah, thank you, Dr. Ilham, especially for moderating this session. Now we come to the end of this tutorial meeting. On behalf of the committee, I would like to thank you for your attendance and participation, especially to the 3 speakers who had shared their knowledge on SAR and its application. The e-certificate is available from the link given in the chat room. Finally, see you next time in other occasion. Goodbye. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Okay, thank you very much for Nisa. I think that's conclude our session for today, and the link of certificates, as Nisa mentioned, I already put it in the chat room, so you can use it for download your e-certificate. That will be available until 6 p.m. Tonight, until it's closed. Other than that, don't forget to register your name also as part of our record that you have joined this tutorial. I will stop the recording, Sensei, and let the room open for everyone to say hello. Maybe there are some more issues needed to be discussed. you are welcome. Thank you very much once again. As a moderator, I once again would like to thank you for the committee of APSAR who give us an opportunity to host under the name of UNHAS after UGM, after ITB, and also ITS. This is a great opportunity to all these universities to collaborate in terms of the SAR research in the future. Thank you once again. Thank you very much for your time. Assalamualaikum warahmatullahi wabarakatuh.
Yeah, thank you very much, Pak Ilham. Yeah. Yeah. Terima kasih semuanya. Yeah, thank you very much all.
Terima kasih Prof Jos.
Yeah.
Sehat-sehat.
Thank you very much. Yes, keep healthy. Yeah.
Thank you, Prof Josafat.
Yeah, terima kasih. Oh, ini ada Pak.
Ada Pak Fauzan.
Iya, muncul di akhir-akhir saya,
coy.
Pak. Siap apply paper insya Allah, Pak.
Oh ya Pak, anten aja enggak apa-apa Pak yang circular forest. Ya.
Oh, okay, ya. Siap, Prof Josafat. Ya.
Sampai tinggal until 30 June. Yes, it is
yes,
still
possible. Not, ya, oke.
Ya, masih ada 2 mingguan lah,
Prof
masih
Yoyo
bisa
juga.
untuk apply.
Ya, siap.
Yeah.